You are floating through an ocean you cannot see. Right now, as you watch this, the Milky Way is being dragged through space at 600 kilometers per second toward a point we have never observed. Something enormous is pulling us, something invisible, and it has been pulling us for billions of years. We call it the Great Attractor, and it is just one symptom of a much larger problem. 95% of the universe is missing, not hidden behind a distant star, not tucked away in some unreachable dimension, missing from the equations, absent from the instruments, invisible to every telescope humanity has ever built. We can map the cosmic web, a structure so vast it makes galaxies look like grains of sand. We can measure the expansion of space itself, calculate it down to 70 kilometers per second per megaparsec. We can detect the faint whisper of light from 13.8 billion years ago, the afterglow of creation itself. And yet we cannot tell you what 95% of reality is made of. 5%. That is all we see. The stars, the planets, the gas, the dust, your body, every atom that has ever been observed, all of it adds up to 5% of what is actually out there. The rest is split between two forces we have names for but do not understand. Dark matter, the invisible glue holding galaxies together, and dark energy, the mysterious force tearing the universe apart faster every day. Astronomers do not like to admit when they are lost, but right now, cosmology is in crisis. Two measurements of how fast the universe is expanding refuse to agree. Our best model cannot explain what we are seeing, and the deeper we look with our most powerful instruments, the less sense any of it makes. This is the story of the universe we thought we knew, and the 95% that proves we were wrong. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We are seeing only a tiny fraction of reality. That sentence is not speculation. It is not a poetic metaphor. It is a measurement. When astronomers add up everything we can observe in the universe, all the stars, all the planets, all the gas clouds drifting between galaxies, all the light, all the matter that interacts with light in any way whatsoever, the total comes to roughly 5% of what should be there. 5%. The rest, the other 95% of the universe, is something else, something we cannot see, cannot touch, cannot measure directly. We only know it exists because without it, nothing we can see would make sense. The galaxies would fly apart. The universe would not expand the way it does. The structure of everything, the cosmic web of filaments and voids stretching across billions of light years, would never have formed. The visible universe, the one you learnt about in school, the one captured in those breathtaking photographs from Hubble and Webb, is the tip of an iceberg. And the rest of the iceberg is not just hidden. It is something fundamentally different from anything we have ever touched or built or understood. This is not a problem that better telescopes can solve. This is not a gap that will close with a few more years of data. This is a hole in our understanding of reality so large that when cosmologists talk about it honestly, they use words like crisis. Let's start with what we can see, because that is the part of the story that makes sense. The universe you know, the one made of atoms, is called baryonic matter. Baryons are particles like protons and neutrons, the building blocks of atomic nuclei. Everything you have ever seen or touched or tasted is baryonic matter. The chair you are sitting in, the air in your lungs, the sun, the moon, the Andromeda galaxy, the faint glow of nebulae in deep space images, all of it is made of atoms, and all of it together makes up 5% of the total mass and energy in the universe. That 5% is not evenly distributed. Most of it is hydrogen and helium. the simplest and lightest elements, forged in the first few minutes after the Big Bang. A smaller fraction is heavier elements, carbon, oxygen, iron, the elements that make planets and life possible. Those heavier elements were not around in the beginning. They had to be cooked inside stars over billions of years, fused in the crushing heat of stellar cores, then scattered into space when those stars died. Every atom of oxygen in your body, every molecule of water on Earth, came from the death of a star that exploded long before our solar system existed. The visible universe is full of structure. You can see it in photographs. Spiral galaxies with arms curling outward like pinwheels, elliptical galaxies that look like glowing eggs, irregular galaxies smashed and distorted by collisions with their neighbors, nebulae, vast clouds of gas and dust glowing in shades of red and blue and green as newborn stars ionize the material around them, globular clusters, tight swarms of ancient stars packed so densely that their centers look like pools of spilled light. All of this structure, all of this beauty, all of this variety represents 5% of what is out there. For a long time, nobody realized there was a problem. Astronomers in the early 20th century looked at galaxies and saw exactly what they expected. Bright cores, dimmer outskirts, a predictable drop in luminosity as you moved away from the center. If you assumed that light traces mass, which seemed reasonable because stars are massive and stars produce light, then the galaxies made sense. Newton's laws predicted how objects should move in a gravitational field. If most of a galaxy's mass was concentrated in the bright central bulge, then stars in the outer regions should orbit more slowly, the same way Pluto orbits the Sun more slowly than Earth does. The further out you go, the weaker the pull, the slower the orbit. Simple, elegant, wrong. The first crack appeared in 1933. A Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a dense collection of more than 1,000 galaxies located about 320 million light-years from Earth. Zwicky was not a diplomat. He was famously blunt, frequently difficult, and utterly fearless when it came to challenging the scientific consensus. His colleagues called him abrasive. He called them spherical bastards because, he said, they were bastards no matter which way you looked at them. Zwicky measured the velocities of galaxies moving through the Coma cluster by analyzing the Doppler shift in their light. Some galaxies were moving toward us. Their light shifted toward the blue end of the spectrum. Others were moving away. Their light redshifted. By measuring how fast the galaxies were moving, Zwicky could estimate how much mass the cluster needed to contain in order to hold itself together. Gravity is what keeps a galaxy cluster from flying apart. If the galaxies are moving too fast, they should escape. If the cluster's gravity is strong enough, they stay bound. Zwicky did the math and found something wrong. The galaxies in the Coma cluster were moving far too fast. Their velocities were so high that the cluster should have torn itself apart long ago. Unless there was more mass present than he could see. A lot more. Zwicky estimated that the cluster contained roughly 400 times more mass than could be accounted for by its visible galaxies. He called this unseen mass Dunkel Materia, dark matter. Nobody believed him. For decades, Zwicky's observations sat on the shelf. It was strange, yes, but galaxy dynamics were messy and poorly understood, and most astronomers assumed the discrepancy would resolve itself with better data or better models. It did not. In the 1970s, an astronomer named Vera Rubin, working with instrument designer Kent Ford, started measuring the rotation curves of spiral galaxies. A rotation curve is a graph that shows how fast stars and gas are orbiting at different distances from the galactic center. You measure the Doppler shift of light from hydrogen gas clouds at various points along a galaxy's disk, and from that you can calculate the orbital speed at each radius. According to Newtonian gravity, the curve should rise steeply near the center where most of the mass is concentrated, then fall off gradually as you move outward. That is what happens in our solar system. Mercury zips around the Sun at 47 kilometers per second. Earth moves at 30. Neptune crawls at 5. The further out you go, the slower the orbit. Rubin expected galaxies to behave the same way. They did not. She found that stars in the outer regions of spiral galaxies were orbiting just as fast as stars near the center. The rotation curves stayed flat, sometimes even rising slightly, all the way out to the visible edge of the galaxy and beyond. This was not a small effect. This was not a subtle discrepancy that could be explained away with measurement error. This was a glaring, undeniable contradiction of what the visible matter predicted. Either Newton's laws of gravity were breaking down on galactic scales, or there was a massive amount of unseen matter surrounding each galaxy, pulling on the outer stars and keeping them moving faster than they should. Rubin was meticulous. She and Ford measured rotation curves for more than 200 galaxies. The pattern held. Every spiral galaxy they looked at showed the same flat rotation curve. The stars were moving too fast. The galaxies should be tearing themselves apart. They were not. Something invisible was holding them together. Unlike Zwicky, Rubin was diplomatic. She presented her findings carefully, acknowledged uncertainties, and avoided grand claims. The response was still skepticism. Some astronomers suggested that the outer regions of galaxies contained large amounts of dim matter, failed stars, cold gas, black holes, objects that were baryonic but just too faint to see. Others proposed that the laws of gravity needed to be modified at large scales. A theory called modified Newtonian dynamics, or MOD, gained a small but vocal following. It proposed that gravity behaves differently when accelerations are extremely weak, as they are in the outer regions of galaxies. Under MOND, you did not need dark matter, you just needed different physics. For a while, it seemed like a real alternative. Then came gravitational lensing, and the debate ended. Gravitational lensing is one of the most beautiful confirmations of Einstein's general relativity. Einstein predicted that mass warps spacetime, and that light traveling through warped spacetime follows a curved path. In 1919, astronomers observed stars near the Sun during a solar eclipse and confirmed that their positions had shifted slightly, exactly as Einstein predicted. The Sun's gravity had bent the light from those stars as it passed nearby. If a small object, like the Sun, could bend light, a massive object like a galaxy cluster could bend it dramatically. Light from a distant galaxy passing near a foreground cluster would be deflected, smeared, sometimes split into multiple images. The cluster acts like a lens, magnifying and distorting the background galaxy. The amount of distortion depends on how much mass is in the cluster, not how much light. How much mass? In the 1980s and 1990s, astronomers started mapping gravitational lensing around galaxy clusters. They measured the distortions in background galaxies and used that data to calculate the total mass of the foreground cluster. Then they compared that mass to the amount of visible matter, the galaxies, the hot gas glowing in X-rays, everything they could detect with telescopes. The results were unambiguous. The clusters contained far more mass than could be seen, roughly 10 times more in most cases. The invisible mass was not concentrated in the galaxies themselves. It formed enormous diffuse halos surrounding and permeating the clusters. You could map its distribution by mapping the lensing distortions, and when you did, you found that the dark matter was everywhere. It was not some exotic addition to a few weird galaxies. It was the dominant form of matter in the universe. One of the most striking examples came from a system called the Bullet Cluster. In 2006, astronomers observed the aftermath of a collision between two galaxy clusters located about 3.8 billion light-years away. When the clusters collided, the hot gas in each one, which emits X-rays and makes up most of the baryonic mass, slammed together and was slowed by friction. The galaxies themselves, which are tiny compared to the spaces between them, passed through each other mostly undisturbed. And the dark matter, which does not interact with normal matter except through gravity, sailed right through without slowing down. By mapping the X-ray emission from the hot gas and the gravitational lensing from the total mass, astronomers could see where the baryonic matter ended up and where the dark matter went. They were in different places. The dark matter had continued moving forward, separating from the gas. The lensing signal was strongest not where the visible matter was brightest, but where the dark matter halos had drifted. This was the smoking gun. It ruled out most modified gravity theories because modified gravity cannot separate itself from matter. Gravity is a property of spacetime, and spacetime is everywhere. You cannot have gravity in one location and not in another, unless there is mass in one location and not in another. The bullet cluster proved that the unseen mass was real, physical, and distinct from the baryonic matter we can observe. It was not an illusion. It was not a trick of the light. It was there. By the early 2000s, the evidence for dark matter had become overwhelming. Rotation curves, gravitational lensing, galaxy cluster dynamics, computer simulations of cosmic structure formation, all of it pointed to the same conclusion. The universe contains roughly 5 times more dark matter than baryonic matter. Dark matter makes up about 85% of the total matter in the universe. It does not emit light. It does not absorb light. It does not reflect light. It does not interact with electromagnetic forces in any way we have ever detected. It only interacts through gravity. As far as we can tell, it passes through normal matter like a ghost. You could be surrounded by dark matter right now, particles streaming through your body, through the walls of your house, through the entire planet, and you would never feel a thing. The only reason we know it is there is because galaxies would not hold together without it. The only reason we exist is because dark matter was there first, pulling normal matter together into clumps dense enough to form stars. This is where the visible universe stops making sense on its own. Everything you see, every star, every galaxy, every nebula glowing in deep space, is riding on a scaffold made of something we cannot see. The stars are not the foundation, they are the decoration. The galaxies are not the main event, they are tracers, breadcrumbs marking the locations where dark matter has gathered in sufficient quantities to pull baryonic matter inward and ignite fusion. Think about what that means. The Milky Way, our home galaxy, contains somewhere between 100 billion and 400 billion stars. It has a visible diameter of about 100,000 light-years. It weighs roughly 1.5 trillion times the mass of our Sun, if you count only the stars, gas, and dust. But the dark matter halo surrounding the Milky Way extends much further, perhaps 600,000 light-years or more, and it contains roughly 10 times as much mass as all the visible matter combined. We live inside a cloud of invisible material that outweighs everything we can see by an order of magnitude, and we have no idea what it is made of. There are candidates. The leading hypothesis for decades has been WIMPs, weakly interacting massive particles. These would be a new type of fundamental particle, something not included in the standard model of particle physics. WIMPs would have mass, which gives them gravity, but they would interact with normal matter only through the weak nuclear force, one of the 4 fundamental forces of nature. The weak force is responsible for certain types of radioactive decay and operates only at subatomic distances. If WIMPs exist, They would pass through ordinary matter almost all the time, but very occasionally one might collide with an atomic nucleus. Detecting that collision would prove their existence. Dozens of experiments have been built to search for WIMPs, detectors buried deep underground to shield them from cosmic rays, tanks of ultra-pure liquids or crystals held at near absolute zero, watching for the faint flash of energy that would signal a WIMP interaction. So far, nothing. No confirmed detections. Either WIMPs are rarer or more weakly interacting than we hoped, or they are not the answer. Another candidate is the axion, a hypothetical particle originally proposed to solve a different problem in quantum chromodynamics. Axions would be extremely light, perhaps a trillion times lighter than an electron, but they could exist in such enormous numbers that their collective mass would add up to the dark matter we observe. Axion detectors are smaller and work differently, using powerful magnetic fields to convert axions into detectable photons. Again, no confirmed detections yet, but the search continues. There are more exotic possibilities. Primordial black holes, tiny black holes formed in the first fraction of a second after the Big Bang, too small to have formed from collapsing stars. Sterile neutrinos, a hypothetical heavier cousin of the neutrinos we already know exist. Some physicists have even proposed that dark matter is not matter at all, but a modification of space-time itself, a kind of dark fluid with negative pressure that mimics the gravitational effects we observe. In 2018, a researcher named Jamie Farnes published a model suggesting that dark matter and dark energy, the even stranger force we will get to shortly, could both be explained by a single substance with negative mass. Negative mass would gravitationally repel normal matter instead of attracting it, but in certain configurations it could still produce the effects we attribute to dark matter. The model is speculative, untested, and controversial, but it is on the table. At this point, nearly everything is on the table because we are 88 years past Zwicky's first observation and we still do not know what dark matter is. The thing that keeps physicists awake at night is not just that we cannot see dark matter, it is that dark matter seems perfectly designed to be invisible. It does not interact with light. It does not clump together the way normal matter does, because normal matter has electromagnetic forces that let atoms stick to each other, form molecules, condense into planets and stars. Dark matter just drifts. It forms vast diffuse halos. It pulls on galaxies. It shapes the universe. And it does all of this without ever lighting up, without ever leaving a mark we can see directly. It is as if the universe has a parallel structure running through it, a skeleton holding everything in place, and we are only just now realizing it was there all along. The European Space Agency launched a mission called Euclid in 2023 specifically to map the dark universe. Euclid is designed to observe billions of galaxies across more than a third of the sky, measuring their shapes, their distances, and how their light has been distorted by gravitational lensing. The goal is to build the most detailed map ever made of how dark matter is distributed across the cosmos. NASA's James Webb Space Telescope, which began operations in 2021, is also contributing. Webb can see further back in time than any previous telescope, imaging galaxies as they existed when the universe was less than 1 billion years old. By studying how those early galaxies formed and evolved, astronomers hope to understand how dark matter shaped the first structures in the universe. But even with these incredible instruments, we are still looking at shadows. We are still inferring the presence of something we cannot touch. The typical galaxy, when you measure its total mass using rotation curves or gravitational lensing, turns out to weigh roughly 10 times more than the sum of all its visible stars, gas and dust. 10 times. Imagine walking into a room and discovering that 90% of the furniture is invisible. You can bump into it, you can feel its weight, but you cannot see it, cannot photograph it, cannot point to it and say, there it is. That is what astronomers are dealing with every time they observe a galaxy. Most of what is there is missing from the picture. Most of what holds the galaxy together is something we do not understand. And dark matter is only part of the problem. It accounts for roughly 27% of the universe's total mass energy content. That still leaves 68% unaccounted for. 68% of the universe is not dark matter. It is something even stranger. Something that does not just sit there pulling on galaxies. Something that is actively pushing the entire universe apart, faster and faster, in a way that defies every intuition we have about how gravity should work. The visible universe, the 5% we can see and measure and build our lives on, is not just incomplete. It is a thin skin stretched over an abyss we are only beginning to map. The iceberg analogy is almost too gentle, because an iceberg, at least, is made of the same substance above and below the waterline. The universe is not. What we see and what is hidden are made of fundamentally different things, and the hidden part is winning. We have spent decades looking for something we cannot see, and the strangest part is that we have found it. Not directly, not by pointing a telescope at a patch of sky and watching a particle glow, but by elimination, by measuring what should be there, realizing it is not enough, and concluding that something else must be filling the gap. Dark matter is not a substance anyone has ever held in their hands or trapped in a detector. It is a ghost that reveals itself only through the things it does to everything around it. And what it does is hold the universe together. The problem starts small, or at least it started small, when Vera Rubin first noticed it in the 1970s. She was measuring how fast stars orbit within spiral galaxies. This is not exotic work. It is the bread and butter of observational astronomy. You point a spectrograph at a galaxy, measure the Doppler shift of hydrogen emission lines at various distances from the galactic center, and from that you calculate how fast the gas and stars are moving. The expectation was simple. Stars closer to the center of a galaxy should move faster than stars farther out, because most of the galaxy's mass is concentrated in the bright central bulge. That is how our solar system works. Mercury screams around the Sun at nearly 50 kilometers per second. Earth moves at 30. Neptune, out at the edge, crawls along at 5. The farther you are from the mass, the weaker the gravity, the slower the orbit. Isaac Newton worked this out in the 1680s, and it has held up ever since. Rubin expected galaxies to behave the same way. She was wrong. Every galaxy she looked at showed the same bizarre pattern. The stars in the outer regions were moving just as fast as the stars near the center, sometimes faster. The rotation curves, those graphs plotting orbital speed against distance from the galactic core, should have declined smoothly as you moved outward. Instead, they stayed flat all the way out to the visible edge of the galaxy and beyond, as far as the hydrogen gas extended. This was not subtle. This was not a small discrepancy that could be explained away with better instruments or revised models. The outer stars were moving so fast that they should have been flung out of the galaxy entirely. Imagine swinging a ball on a string in a circle above your head. The faster you spin it, the harder you have to grip the string to keep it from flying away. If you let go, the ball shoots off in a straight line. Galaxies were spinning their outer stars fast enough that the visible mass in the galactic center should not have been able to hold on, and yet the galaxies were not falling apart. The stars were not escaping. Something was gripping the string. Rubin was not the first to notice the problem. Fritz Zwicky had stumbled onto it decades earlier in 1933 while studying the Coma cluster, a dense swarm of more than 1,000 galaxies located about 320 million light-years away. Zwicky measured how fast individual galaxies were moving through the cluster by analyzing the Doppler shifts in their light. Some were moving toward us, their light shifted blue. Others were receding, their light shifted red. By averaging those velocities, Zwicky could estimate the total mass of the cluster. He used a straightforward principle. If you know how fast objects are moving and how tightly they are bound together, you can calculate how much gravity is needed to keep them from flying apart. The galaxies in the Coma cluster were moving fast, too fast. Zwicky calculated that the cluster needed to contain roughly 400 times more mass than could be accounted for by its visible galaxies in order to hold itself together. 400 times. He called the missing mass Dunkel Materie, dark matter, and published his findings in a Swiss journal. Almost nobody paid attention. Zwicky had a reputation for being difficult. He was brilliant, no question, but he alienated colleagues, picked fights, and made grand claims that other astronomers found hard to swallow. His dark matter hypothesis sounded too strange, too radical. Surely the explanation was simpler. Maybe there were large amounts of dim matter scattered through the cluster. Failed stars, cold gas, black holes, objects that were too faint to see but still made of ordinary atoms. The assumption was that if you looked harder, you would find the missing mass. Nobody looked harder. The problem sat on the shelf for 40 years. Rubin brought it back. She was careful where Zwicky had been brash. She worked with Kent Ford, an astronomer and instrument designer who had built one of the most sensitive spectrographs in the world. Together, they measured rotation curves for more than 200 spiral galaxies. Every single one showed the same flat curve. The pattern was universal. It was not a quirk of one or two strange galaxies. It was happening everywhere, and the implications were unavoidable. Either the laws of gravity were breaking down at galactic scales, or galaxies contained enormous amounts of unseen mass. Rubin favored the second explanation. She proposed that every spiral galaxy was embedded in a massive halo of dark matter, a roughly spherical cloud of invisible material extending far beyond the visible disk. The dark matter would not emit or absorb light, so it would not show up in photographs, but its gravity would pull on the outer stars, keeping them moving faster than they otherwise would. The mass of this halo would have to be substantial. Roughly 10 times the mass of all the visible stars, gas and dust combined. 10 times. That is not a correction. That is a complete rewrite of what a galaxy is. The response was skepticism. Some astronomers argued that the outer regions of galaxies might contain large amounts of baryonic matter that was simply too dim to detect. Brown dwarfs, for instance, are failed stars that never ignited fusion. They emit almost no light. If galaxies were littered with billions of brown dwarfs, that could account for the missing mass. Others pointed to clouds of cold molecular hydrogen, which also emit very little light. Still others suggested that Rubin's measurements were being affected by uncertainties in the distances to the galaxies she was studying. If the distances were off, the calculated masses would be off, and the rotation curves might not be as anomalous as they appeared. Rubin was patient. She refined her measurements. She and Ford observed galaxies at different wavelengths, using radio telescopes to trace the distribution of neutral hydrogen gas far beyond the visible disk. The flat rotation curves persisted. They extended out to distances where there was no plausible reservoir of dim baryonic matter left. The halos were too large, too diffuse, too massive to be explained by anything made of ordinary atoms. The only explanation that fit the data was something new, something that did not interact with light, something that did not clump together the way normal matter does, because normal matter has electromagnetic forces that let atoms stick to each other, condense into clouds, collapse into stars. Dark matter, whatever it was, seemed to lack those forces. It only interacted through gravity. It formed vast, smooth halos that surrounded galaxies like invisible scaffolding, and it outweighed everything we could see. The breakthrough came from gravitational lensing. This is one of the cleanest, most direct ways to measure mass, because it does not rely on assumptions about what kind of matter is present. It only cares about gravity. Einstein's general relativity predicts that mass warps spacetime, and light traveling through warped spacetime follows a curved path. A massive object, like a galaxy cluster, can act as a lens, bending the light from more distant galaxies behind it. The amount of bending depends on the total mass of the lens, not just the visible mass. In the 1980s and 1990s, astronomers started systematically mapping gravitational lensing around galaxy clusters. They measured the distortions in the shapes of background galaxies, those faint smudges and arcs that appear in deep images of the sky, and used that data to calculate how much mass was present in the foreground cluster. Then they compared that mass to the amount of visible matter, the galaxies themselves and the hot gas glowing in X-rays. The results were consistent across dozens of clusters. The total mass was roughly 10 times greater than the visible mass. The invisible component was not concentrated in the galaxies. It formed enormous diffuse halos that extended far beyond the regions where stars and gas were found. You could map the distribution of dark matter by mapping the lensing distortions, and when you did, you found that the dark matter halos were larger and more extended than the visible clusters. The galaxies were just bright spots embedded in a much larger structure. One of the most striking examples of gravitational lensing came from a system called the Bullet Cluster. In 2004, astronomers observed the aftermath of a collision between two galaxy clusters located about 3.8 billion light-years away. The collision had happened roughly 150 million years earlier, but we were only now seeing the light from it because of the time it takes for photons to travel across that distance. When the clusters collided, the hot gas in each one, which makes up most of the baryonic mass, slammed together and was slowed by friction. You could see this in X-ray images taken by NASA's Chandra X Ray Observatory. The gas formed two bright clumps in the middle of the collision site, glowing at millions of degrees as it was compressed and heated by the impact. The galaxies themselves, which are tiny compared to the spaces between them, passed through each other mostly undisturbed. Galaxies are mostly empty space. A collision between two galaxy clusters is really a collision between the gas clouds that fill the space between the galaxies. The stars just drift through like ships passing in the night. But the dark matter, which does not interact with normal matter except through gravity, sailed right through without slowing down. It did not collide. It did not compress. It did not heat up. It just kept moving. By mapping the gravitational lensing around the Bullet Cluster, astronomers could see where the total mass was located. The lensing signal was strongest not where the hot gas was brightest, but where the dark matter halos had drifted after passing through each other. The two components had separated. The visible matter was in one place, the invisible matter was somewhere else. This was the smoking gun. It ruled out most alternative explanations that tried to avoid invoking dark matter. Theories like modified Newtonian dynamics, or MOND, which proposed that gravity behaves differently at low accelerations, could not explain the Bullet Cluster. MOND is a modification of the laws of physics, not a new type of matter. You cannot separate the laws of physics from the stuff they govern. Gravity is a property of space-time itself. If you modify gravity, the modification applies everywhere. You cannot have modified gravity in one location and normal gravity in another. unless there is mass in one location and not in another. The bullet cluster proved that there was mass where no visible matter existed. The dark matter was real. It was physical. It was there. By the early 2000s, the evidence had piled up to the point where denying the existence of dark matter required ignoring a mountain of independent observations: rotation curves, gravitational lensing, galaxy cluster dynamics, the cosmic microwave background. That last one deserves its own explanation because it is arguably the most powerful piece of evidence we have. The cosmic microwave background, or CMB, is the faint afterglow of radiation left over from the Big Bang. It was emitted roughly 380,000 years after the universe began, at the moment when the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was opaque, a hot plasma where photons were constantly scattering off free electrons. After that moment, the photons were free to travel in straight lines. The CMB is a snapshot of the universe at that instant, a baby picture taken when the cosmos was less than 400,000 years old. The light has been traveling toward us ever since, stretched by the expansion of the universe from visible wavelengths into the microwave part of the spectrum. Today, the CMB has a temperature of about 2.7 degrees above absolute zero. It is incredibly uniform. If you measure the temperature of the CMB in one part of the sky and compare it to the temperature in another part, the difference is only about 1 part in 100,000. But those tiny variations are everything. They are the seeds of all the structure we see in the universe today. Regions that were slightly denser than average in the early universe had slightly stronger gravity. Over time, matter flowed into those regions, amplifying the initial density contrasts. The denser regions eventually collapsed to form galaxies, galaxy clusters, and the vast cosmic web of filaments that stretch across billions of light years. The pattern of temperature fluctuations in the CMB encodes information about the composition of the universe at that early time. By analyzing that pattern, cosmologists can calculate how much ordinary matter was present, how much dark matter, how much dark energy, and a host of other parameters that describe the universe's behavior. The results are startlingly precise. The universe is roughly 4.9% ordinary baryonic matter, 26.8% dark matter, and 68.3% dark energy. Those numbers come from data collected by NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, and later refined by the European Space Agency's Planck satellite. Planck mapped the CMB with unprecedented resolution and sensitivity. The error bars on the measurements are small. The universe contains roughly 5 times more dark matter than ordinary matter. That is not a guess. That is a measurement. The CMB tells us something else too. It tells us that dark matter was there from the beginning. The fluctuations in the CMB are too small to have been caused by ordinary matter alone. Baryonic matter interacts with radiation. Photons scatter off protons and electrons. That scattering smooths out density contrasts, erasing structure on small scales. If the early universe had been made only of baryonic matter, the temperature fluctuations in the CMB would have been too weak to seed the galaxies we see today. Dark matter does not interact with radiation. It does not scatter photons. It only interacts through gravity. That means dark matter could clump together without being smoothed out by radiation. It could start pulling ordinary matter inward long before the CMB was emitted. By the time the universe became transparent, 380,000 years after the Big Bang, dark matter had already seeded the first structures. The galaxies formed where the dark matter had gathered. The stars lit up inside the dark matter halos. The visible universe is built on a framework of invisible material that was in place before the first atoms even existed in their current form. We are not just surrounded by dark matter, we are living inside structures that dark matter created. So what is it? That is the question that has consumed physicists for decades. We know dark matter exists, we know how much of it there is, we know how it behaves. But we do not know what it is made of. The leading candidate for a long time has been WIMPs, weakly interacting massive particles. These would be a new type of fundamental particle, something not included in the standard model of particle physics. The standard model describes all the known particles and forces in the universe, the electrons, quarks, photons, neutrinos, and the forces that govern their interactions. It is one of the most successful theories in the history of science. It has been tested to absurd levels of precision, and it does not include dark matter. WIMPs would fill that gap. They would have mass, which gives them gravity, but they would interact with ordinary matter only through the weak nuclear force, one of the four fundamental forces of nature. The weak force is responsible for certain types of radioactive decay. It operates only at subatomic distances. If WIMPs exist, they would pass through ordinary matter almost all the time. Billions of them could be streaming through your body right now, passing through the atoms in your skin, your bones, your organs, without ever touching anything. But very occasionally, one might collide with an atomic nucleus. That collision would deposit a tiny amount of energy, enough to cause a faint flash of light or a measurable recoil in a detector. Dozens of experiments have been built to search for that signal, detectors buried deep underground to shield them from cosmic rays, tanks of ultra-pure liquids, xenon or argon, held at temperatures near absolute zero, arrays of crystals that scintillate when a particle passes through. The detectors sit in the dark, waiting. They have been waiting for decades. So far, nothing. No confirmed detections. There have been hints, anomalies, signals that briefly excited the community before being explained away as background noise or instrumental artifacts. But no definitive, reproducible detection of a WIMP. Either WIMPs are rarer or more weakly interacting than we hoped, or they are not the answer. Another candidate is the axion. This is a hypothetical particle originally proposed in the 1970s to solve a different problem in quantum chromodynamics, the theory that describes the strong nuclear force. Axions would be extraordinarily light, perhaps a trillion times lighter than an electron, but they could exist in such enormous numbers that their collective mass would add up to the dark matter we observe. Axion detectors work differently from WIMP detectors. They use powerful magnetic fields to convert axions into photons, which can then be detected. The Axion Dark Matter Experiment, or ADMX, has been running for years at the University of Washington, scanning different mass ranges in the search for axion signals. Like the WIMP searches, it has come up empty so far, but the parameter space is vast. There are many possible masses and interaction strengths to explore. The search continues. A third possibility is primordial black holes. These would be black holes that formed in the first fraction of a second after the Big Bang, not from the collapse of massive stars, but from density fluctuations in the primordial plasma. If the early universe had regions that were dense enough, they could have collapsed directly into black holes without ever forming stars. Primordial black holes could span a wide range of masses, from microscopic to thousands of times the mass of the Sun. If enough of them exist, they could account for some or all of the dark matter. This idea fell out of favor in the 1990s when surveys using gravitational microlensing, a technique that detects dark, compact objects passing in front of background stars, failed to find large populations of such objects in the Milky Way's halo. But primordial black holes have made a comeback in recent years. Some researchers have suggested that the black holes detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO, could be primordial rather than stellar in origin. The jury is still out. There are more speculative ideas. Sterile neutrinos, hypothetical particles that are heavier than the neutrinos we know exist and interact even more weakly with ordinary matter. Dark photons, a proposed counterpart to ordinary photons that would mediate a new type of force acting only on dark matter. Some physicists have even proposed that dark matter is not a particle at all, but a modification of space-time itself, a kind of topological defect or field that mimics the gravitational effects we observe. In 2018, a researcher named Jamie Farnes published a model suggesting that dark matter could be explained by a form of matter with negative mass. Negative mass would gravitationally repel normal matter, but in certain configurations, it could still produce the effects we attribute to dark matter halos. The model is untested and controversial, but it is on the table. At this stage, nearly everything is on the table because we are 90 years past Zwicky's first observation and we still do not know what we are looking for. What we do know is that dark matter is everywhere. It is not hiding in some exotic corner of the universe. It is threaded through every galaxy, every cluster, every filament in the cosmic web. The Milky Way sits inside a dark matter halo that extends perhaps 600,000 light-years from the galactic center, far beyond the visible disk. That halo contains roughly 10 times as much mass as all the stars, gas, and dust in the galaxy combined. The Sun orbits through that halo at about 220 kilometers per second, and as it does, dark matter particles are streaming through the solar system in every direction. They pass through the Earth. They pass through you. If WIMPs are the answer, then roughly 1 billion of them pass through every square centimeter of your body every second. You do not feel them. They do not leave a mark. They interact so weakly with ordinary matter that they might as well be ghosts. But they are there. And without them, the galaxy would not exist. The Milky Way would have flown apart billions of years ago, its stars scattered into the void. The solar system would never have formed. The Earth would not exist. Neither would you. Dark matter is not just a curiosity. It is the foundation on which everything we see is built. The European Space Agency launched a mission called Euclid in 2023 specifically to map the distribution of dark matter across the universe. Euclid carries a visible light camera and a near-infrared spectrograph. Its job is to observe billions of galaxies across more than a third of the sky, measuring their shapes, their distances, and how their light has been distorted by gravitational lensing. By analyzing those distortions, astronomers will build a three-dimensional map of dark matter halos spanning billions of light-years. That map will show how dark matter has shaped the evolution of cosmic structure over the past 10 billion years. It will test our models of how galaxies form and evolve. It will constrain the properties of dark energy, the even stranger force that is accelerating the universe's expansion. And it might, just might, reveal something unexpected, a clue that points toward what dark matter actually is. NASA's James Webb Space Telescope is contributing as well. Webb can see further back in time than any previous telescope, imaging galaxies as they existed when the universe was less than 1 billion years old. By studying how those early galaxies formed and how dark matter influenced their evolution, astronomers hope to understand the role dark matter played in the first few 100 million years after the Big Bang. Those observations are already underway, and the data is beginning to come in. The typical spiral galaxy, when you add up all its visible stars, gas, and dust, weighs somewhere between 100 billion and a few trillion times the mass of our Sun. The dark matter halo surrounding that galaxy weighs 10 times more, 10 times. Imagine living your entire life in a city and then discovering that 90% of the buildings are invisible. You have been walking past them, bumping into them, navigating around them your whole life, and you never knew they were there. That is what astronomers are dealing with. Most of what holds galaxies together, most of what shapes the structure of the universe, is something we cannot see. And despite decades of searching, despite building the most sensitive detectors ever constructed, despite looking in every corner of the electromagnetic spectrum and beyond, we still do not know what it is. We only know what it does. It holds galaxies together. It seeds the formation of structure. It shapes the orbits of stars, and it passes through us without leaving a trace. Dark matter is the invisible glue that binds the universe, and we are still trying to figure out what it is made of. But dark matter, as strange and pervasive as it is, only accounts for about 27% of the universe. The other 68% is not matter at all. It is something even more baffling, something that does not pull galaxies together, something that pushes them apart. We have spent decades trying to understand why the universe is held together by something we cannot see, and just when physicists thought they had a handle on that problem, just when dark matter was beginning to make sense as the invisible scaffold holding galaxies in place, the universe delivered a second punch. This one was worse, because dark matter, at least, behaves the way matter is supposed to behave. It has mass. It has gravity. It pulls things together. The second punch does the opposite. It pushes, and it is winning. In 1998, two independent teams of astronomers were racing to measure how fast the universe's expansion was slowing down, not whether it was slowing down. That was assumed. Gravity pulls everything together. The universe is full of matter. Matter has mass. Mass generates gravity. Therefore, the expansion that began with the Big Bang should be gradually losing steam, slowed by the collective gravitational pull of everything in the cosmos. The only question was how much it had slowed. Was the universe decelerating gently, destined to expand forever but at an ever-decreasing rate? Or was it decelerating sharply, headed for an eventual collapse back in on itself? A big crunch that would end the universe in a mirror image of the Big Bang. Both outcomes were on the table. Both were consistent with the known laws of physics. The teams were trying to figure out which one was true. What they found instead was that the universe was not slowing down at all. It was speeding up. The discovery came from supernovae. Not just any supernovae. Type Ia supernovae. A specific class of stellar explosion that happens when a white dwarf star, the dense remnant left behind after a sun-like star burns through its fuel, accretes enough matter from a companion star to push it over a critical mass threshold. When a white dwarf crosses that threshold, roughly 1.4 times the mass of our Sun, it collapses and detonates in a runaway nuclear explosion. Every Type Ia supernova detonates at roughly the same mass, which means every Type Ia supernova reaches roughly the same peak brightness. Astronomers call these objects standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it is. The math is straightforward. Light spreads out as it travels, dimming with the square of the distance. An object twice as far away appears 4 times dimmer. An object 10 times farther appears 100 times dimmer. Measure the apparent brightness, compare it to the known true brightness, and you have the distance. Type Ia supernovae are bright enough to be seen across billions of light years. That makes them ideal for mapping the expansion history of the universe. If you find a Type Ia supernova in a distant galaxy, You can measure how far away it is and how fast that galaxy is moving away from us by measuring the redshift of its light. Do that for dozens of supernovae at different distances, and you can reconstruct how fast the universe was expanding at different points in its history. Compare the expansion rate in the distant past to the expansion rate today, and you can measure how much the expansion has slowed over time. Two teams set out to do exactly that. One was the Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University. Both teams spent years hunting for distant supernovae using ground-based telescopes and the Hubble Space Telescope. Both teams developed sophisticated techniques for identifying Type Ia supernovae in images of distant galaxies, measuring their light curves, the graphs showing how their brightness changed over time, and calculating their distances. It was painstaking work. Type Ia supernovae are rare. You might see one per galaxy per century. To find enough of them to draw meaningful conclusions, you have to survey thousands of galaxies and wait for the explosions to happen. Both teams did. By 1998, Perlmutter's group had measured distances and redshifts for 42 supernovae. Schmidt and Rees had measured 16. The two teams were rivals, competing to publish first, but they were using the same methods and looking at the same type of objects. The expectation was that their results would agree. They did, just not in the way anyone expected. The supernovae were too dim, not by a little, by enough that it mattered. If the universe's expansion had been slowing down over time, the distant supernovae should have appeared slightly brighter than they would in a universe expanding at a constant rate. That is because a decelerating universe means that galaxies in the past were moving away from us more slowly than their current distances would suggest. Slower recession means less distance traveled, which means the light from those galaxies has not dimmed as much. Brighter supernovae mean a slowing universe. Dimmer supernovae mean an accelerating universe. The supernovae were dimmer. Both teams checked their data, they checked their calibrations, they checked their assumptions about dust, about the properties of the supernovae themselves, about whether high redshift Type Ia explosions might be intrinsically different from nearby ones. Nothing explained the discrepancy. The simplest explanation, the one that fit the data without invoking exotic new physics or systematic errors, was that the distant supernovae were farther away than they should be if the universe had been slowing down. They were farther away because the universe had been speeding up. Somewhere around 5 or 6 billion years ago, the expansion of the universe stopped decelerating and started accelerating. The cosmos was not coasting to a stop, it was stepping on the gas. Adam Rees later described the moment he realized what the data were telling him. He was sitting at his computer, running through the analysis for the 16th time, convinced he had made a mistake. The numbers kept coming out the same. The universe was accelerating. He thought, this cannot be right. Then he thought, what if it is? He called Brian Schmidt. Schmidt's reaction was disbelief, followed by a demand to check everything again. They checked. The numbers held. Perlmutter's team came to the same conclusion independently. In 1998, both groups published their findings. The universe was not just expanding, it was expanding faster and faster, and no one had any idea why. The discovery was so unexpected, so contrary to every prediction, that the first reaction in the broader physics community was skepticism. Some astronomers argued that the dimming of the supernovae could be explained by dust in the intervening space absorbing their light. Others suggested that distant supernovae might be intrinsically fainter than nearby ones for reasons no one understood yet. Still others proposed that the cosmological models being used to interpret the data were wrong. that the universe's geometry was more complicated than anyone assumed. Over the next few years, those objections were systematically addressed. Dust absorbs blue light more than red light. If dust were the culprit, distant supernovae would appear redder as well as dimmer. They did not. Observations of supernovae in the infrared, where dust has less effect, showed the same dimming pattern. The intrinsic brightness argument was harder to rule out, but as more supernovae were measured, the pattern held across a wide range of redshifts and galaxy types. The models were tested and refined. Every alternative explanation was examined. None of them worked. By the early 2000s, the evidence had become overwhelming. The universe was accelerating, and the only way to explain that was to invoke something new. Physicists called it dark energy, not because they knew what it was, but because they needed a name for whatever was causing the acceleration. Dark energy is not matter. It does not clump. It does not form halos around galaxies. It does not interact with anything except space-time itself. As far as we can tell, it is spread uniformly throughout the universe, a smooth background that fills every cubic meter of space with the same constant energy density. And that energy has a very strange property. It has negative pressure. Positive pressure, the kind you experience when you inflate a balloon or compress a gas, pushes outward on the walls of a container. Negative pressure pulls inward. But in the context of general relativity, negative pressure has a counterintuitive effect. It causes space-time itself to expand. The more dark energy there is, the faster the expansion. And because the universe is getting bigger, there is more volume for dark energy to fill, which means more total dark energy, which means even faster expansion. It is a runaway process. The universe accelerates because dark energy makes it expand. The expansion creates more space. More space contains more dark energy. More dark energy accelerates the expansion further. Rinse and repeat for the rest of eternity. This was not entirely unprecedented. Albert Einstein had encountered something similar in 1917 when he tried to apply his newly developed theory of general relativity to the universe as a whole. At the time, the prevailing belief was that the universe was static. It did not expand or contract. It just sat there, eternal and unchanging. But Einstein's equations said otherwise. General relativity predicted that a universe filled with matter could not be static. Gravity would pull everything together, causing the universe to collapse. Einstein found this conclusion unacceptable. He believed the universe was stable, so he added a term to his equations, a constant he called lambda, the cosmological constant. Lambda represented a kind of energy inherent to empty space itself, a repulsive force that pushed outward and exactly balanced the inward pull of gravity. With lambda in place, Einstein's equations allowed for a static universe, problem solved. Except it was not. In 1929, Edwin Hubble discovered that the universe was not static at all. It was expanding. Hubble measured the distances to nearby galaxies using Cepheid variable stars, a type of pulsating star whose brightness varies in a regular pattern tied to its intrinsic luminosity. By measuring the period of a Cepheid's pulsation, you could calculate how luminous it truly was. Compare that to how bright it appeared from Earth, and you had the distance. Hubble measured distances to dozens of galaxies and compared those distances to the galaxies' velocities, which he determined by measuring the redshift of their light. He found a clear relationship. The farther away a galaxy was, the faster it was moving away from us. The universe was expanding. When Einstein learned of Hubble's discovery, he immediately recognized that his static universe model was wrong. The cosmological constant, lambda, was unnecessary. He reportedly called it the biggest blunder of his career. He removed lambda from his equations and never spoke of it again. For the next 70 years, lambda was dead and buried. Physicists assumed the universe was expanding but decelerating, slowed by the gravitational pull of all the matter it contained. Then came the supernova results in 1998, and lambda came roaring back, because dark energy behaves exactly like Einstein's cosmological constant. It is a constant energy density that fills all of space. It generates negative pressure. It causes the universe to accelerate. The equations Einstein wrote in 1917, the ones he thought were his biggest mistake, turned out to describe the dominant component of the universe. Lambda was not a blunder. It was a prediction that arrived 80 years too early. The simplest explanation for dark energy is that it is vacuum energy, the energy of empty space itself. Quantum field theory, the framework that describes how particles and forces behave at the smallest scales, predicts that even a perfect vacuum is not truly empty. It seethes with quantum fluctuations, pairs of particles and antiparticles constantly popping into existence and annihilating each other in fractions of a second. These fluctuations carry energy. Add up all the energy from all the fluctuations in a given volume of space, and you get a number. That number is the vacuum energy. According to quantum field theory, vacuum energy should act exactly like a cosmological constant. It should fill space uniformly. It should generate negative pressure. It should cause the universe to accelerate. In principle, this is a solved problem. Dark energy is just vacuum energy. The cosmological constant is the energy of the quantum vacuum. Case closed, except for one small issue. When physicists actually calculate how much vacuum energy there should be, the number they get is wrong. Not slightly wrong, catastrophically wrong. The predicted value of vacuum energy is roughly 10 to the power of 120 times larger than the observed value. That is a 1 followed by 120 zeros. It is the worst prediction in the history of physics. If the vacuum energy were truly that large, the universe would have accelerated so violently in the first fraction of a second after the Big Bang that no structures, no galaxies, no stars, nothing could ever have formed. Space would have expanded faster than light could travel through it. Matter would have been diluted into absolute nothingness before atoms even had a chance to exist. The fact that we are here, that galaxies exist, that you are watching this, means the vacuum energy cannot be anywhere close to the value quantum field theory predicts, but we have no idea why. This is called the cosmological constant problem, and it is one of the deepest unsolved puzzles in theoretical physics. The vacuum should be screaming with energy. Instead, it whispers, and no one knows why. Some physicists have proposed that dark energy is not a cosmological constant at all. Maybe it is something dynamic, a field that changes over time. This idea is called quintessence, named after the classical fifth element that ancient philosophers believed filled the heavens. In quintessence models, dark energy is not a fixed property of space. It is a field, similar to the fields that describe other forces and particles in physics, that slowly rolls down a potential energy curve. As the field evolves, its energy density and pressure change. In some versions, quintessence could cause the universe to accelerate now but decelerate in the future, or vice versa. In others, it could vary from place to place, making the universe expand faster in some regions than in others. The problem with quintessence is that there is no evidence for it. Every measurement of dark energy so far is consistent with it being a cosmological constant. Its energy density appears to be the same everywhere. It does not seem to change over time. That does not rule out quintessence. The changes could be too slow or too subtle to detect with current instruments, but as of now, the simplest explanation is that dark energy is just lambda, a constant, a number in the equations, a feature of spacetime that we do not understand but cannot ignore. In 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating expansion of the universe. The Nobel Committee noted that the discovery had fundamentally changed our understanding of the cosmos. It had revealed that ordinary matter and dark matter together make up less than a third of the universe's total mass and energy. The rest, the dominant component, was something entirely different, something that did not cluster into galaxies or stars, something that pushed instead of pulled, something that was accelerating the universe toward a future no one had predicted. Because if dark energy continues to behave the way it has for the past 5 billion years, the universe is headed for a cold, lonely end. The galaxies will drift farther and farther apart. The space between them will expand faster than light can travel. Eventually, galaxies outside our local group, the small cluster of galaxies that includes the Milky Way and Andromeda, will recede beyond the cosmic horizon. Their light will be stretched to infinite wavelengths. They will disappear from view, not because they stopped existing, but because the space between us and them will be expanding faster than their light can cross it. In 1 trillion years, an observer in the Milky Way will look out into the night sky and see almost nothing, a handful of nearby galaxies slowly merging with our own. Beyond that, darkness. The cosmic microwave background, that faint glow left over from the Big Bang, will have been stretched into invisibility. Future astronomers will have no way of knowing the universe was ever anything other than a small island of stars surrounded by an infinite void. The stars themselves will not last. They will burn through their fuel and die. The largest stars will explode as supernovae, scattering their remains into space. Smaller stars like our Sun will swell into red giants, then shed their outer layers and collapse into white dwarfs. Over trillions of years, star formation will slow and eventually stop as the gas clouds that fuel it are exhausted. The galaxies will grow darker. Eventually, the only objects left will be white dwarfs, neutron stars, black holes, and planets drifting through the void. The white dwarfs will cool. The neutron stars will radiate away their heat. The black holes will evaporate through Hawking radiation, a process so slow that the smallest black holes will take 10 to the power of 67 years to vanish. The largest, like the supermassive black holes at the centers of galaxies, will take 10 to the power of 100 years. That is a 1 followed by 100 zeros. A span of time so vast that calling it incomprehensible is an understatement. And at the end of it, the universe will be cold, dark, and empty. A void filled with nothing but photons, stretched to infinite wavelengths and particles so far apart that they will never interact again. This is called the Big Freeze. It is the most likely future given what we currently know about dark energy. It is not dramatic. There is no final explosion, no collapse, no grand finale. The universe just fades like a candle burning down in an empty room until there is nothing left but silence and stillness. But that is not the only possibility. If dark energy is not constant, if it is something like quintessence and its density increases over time, the universe could be headed for something far stranger. Some models predict a scenario called the Big Rip. In this version, dark energy does not just push galaxies apart. It gets stronger. As space expands, the energy density rises. The expansion accelerates faster and faster. Eventually, the acceleration becomes so extreme that it begins to tear apart structures that gravity is holding together. First, galaxy clusters are ripped apart, then galaxies themselves, then solar systems, then planets. Then, in the final moments, molecules, atoms, and even atomic nuclei are shredded by the expansion of space. The universe does not fade, it tears itself to pieces. current observations suggest this is unlikely. The data are consistent with dark energy being a cosmological constant, which means its density stays the same as the universe expands. But we cannot rule it out. We do not know enough about what dark energy is to say with certainty how it will behave billions of years from now. There is a third possibility. Some theorists have proposed that dark energy could eventually decay, dumping its energy into matter and radiation in a final cataclysmic event. Others have suggested that the laws of physics themselves could change, that the constants we take for granted, the speed of light, the strength of gravity, could drift over time in ways we have not yet detected. These ideas are speculative, they are not supported by current observations. But they are on the table because we are working with a nearly complete absence of understanding about what dark energy actually is. We know it makes up 68% of the universe. We know it is causing the universe to accelerate. We know it has been the dominant component of the cosmos for the past 5 billion years, and that is about it. We do not know what it is made of. We do not know where it came from. We do not know whether it will last forever or change in the future. We are flying blind. What makes this especially frustrating is that dark energy only became dominant relatively recently. For the first 9 billion years of the universe's history, matter, both ordinary and dark, was the dominant component. Gravity ruled. The universe was decelerating. Dark energy was always there, but its density was too low to matter. Then, around 5 or 6 billion years ago, the balance shifted. The universe had expanded enough that the density of matter had dropped below the constant density of dark energy. At that point, dark energy took over. The universe stopped slowing down and started speeding up. The timing is curious. Why did dark energy become dominant just a few billion years before intelligent life emerged to notice it? If it had taken over earlier, galaxies might not have had time to form. If it had taken over later, we might not have discovered it yet. Some physicists argue this is just a coincidence. Others point to it as evidence of the anthropic principle, the idea that we observe the universe having the properties it does, because if it had different properties, we would not be here to observe it. That argument makes some physicists deeply uncomfortable. It feels less like an explanation and more like giving up, but at the moment we do not have a better answer. The discovery of dark energy has forced cosmologists to confront the possibility that we are missing something fundamental about the universe. General relativity has been tested to extraordinary precision. It works. It describes the motion of planets, the bending of light around massive objects, the inspiral of binary black holes, the ripples in space-time we call gravitational waves. It gets everything right. Except it does not predict dark energy. Quantum field theory is the most successful theory in the history of physics. It has been tested to parts per billion. It describes the behavior of particles and forces with absurd accuracy, except it predicts a vacuum energy that is 10 to the power of 120 times too large. The two foundational theories of modern physics, the ones that describe gravity and quantum mechanics, do not agree on what dark energy should be. One of them is missing something, or both of them are, and until we figure out what, we are stuck. The James Webb Space Telescope and the European Space Agency's Euclid mission are both collecting data that will help refine our measurements of dark energy's properties. They are mapping how the expansion rate of the universe has changed over time by observing distant galaxies and supernovae at a range of redshifts. They are measuring the clustering of galaxies and how gravitational lensing distorts their shapes, both of which are sensitive to the effects of dark energy. The goal is to determine whether dark energy truly is a cosmological constant or whether there are hints that it is something more dynamic. Even a tiny deviation from constant behavior would be a major clue. It would point toward new physics, a new field, a new force, something that could eventually lead to a deeper understanding of what dark energy is. So far, the data are consistent with lambda. The universe continues to behave as if it is filled with a constant energy density that does not change. That is both reassuring and frustrating. Reassuring because it means our models are working. Frustrating because it gives us no hints about what comes next. What we do know is that the discovery of dark energy has rewritten the story of the universe. For most of cosmic history, the universe was a battleground between the inward pull of gravity and the outward push of the Big Bang's initial expansion. Gravity was losing, but slowly. The universe was expanding, but the expansion was decelerating, gradually winding down like a ball rolling up a hill. Then, 5 billion years ago, something changed. A new force took over. The hill vanished. The ball started rolling downhill, picking up speed, and it has been accelerating ever since. The universe is not winding down, it is ramping up, and the farther into the future you look, the faster it gets. This is the universe we live in, not the one we expected, not the one the equations predicted when Einstein first wrote them down. Not the one Hubble thought he was discovering when he measured the redshifts of galaxies in the 1920s. The universe is stranger, more dynamic, and more mysterious than any of those pioneers imagined, and the more precisely we measure it, the stranger it gets. Because even the discovery that the universe is accelerating has not settled the debates. It has opened new ones. When astronomers use different methods to measure how fast the universe is expanding today, they get different answers. The disagreement is small, only about 8 or 9%, but it is persistent. It has been confirmed by multiple independent teams using multiple independent techniques, and it refuses to go away. The universe, it seems, is not content to reveal its secrets quietly. It insists on keeping us guessing. When astronomers use different methods to measure how fast the universe is expanding right now, they get different answers. That sentence should not be true. They are measuring the same universe. They are using the most precise instruments humanity has ever built. They are following the same laws of physics, and they are coming up with numbers that do not agree, not by a little, by enough, that after more than a decade of checking and rechecking and refining and remeasuring, the gap has not closed. It has widened. What started as a mild curiosity in the early 2000-teens has metastasized into what physicists now openly call the Hubble tension. Some have started using a different word, crisis. The number at the center of this fight is called the Hubble constant, named after Edwin Hubble, who in 1929 discovered that the universe is expanding. The Hubble constant tells you how fast space is stretching at this exact moment. It is usually written in units of kilometers per second per megaparsec, which sounds terrible until you translate it. A megaparsec is about 3.26 million light-years. The Hubble constant tells you how much faster a galaxy is moving away from us for every additional megaparsec of distance. If the Hubble constant is 70, then a galaxy 3.26 million light-years away is receding at 70 kilometers per second. A galaxy twice as far, 6.5 million light-years away, is receding at 140 kilometers per second. A galaxy 10 times farther is receding at 700 kilometers per second. The relationship is linear. Double the distance, double the speed. This is not because the galaxies are moving through space. It is because space itself is expanding. The farther away a galaxy is, the more space there is between us and it, and the more expansion is happening in that space. The Hubble constant is the expansion rate. It is one of the most important numbers in cosmology because it sets the scale for everything. It determines the size of the observable universe. It determines the age of the universe. It determines how fast structures are drifting apart and how long we have before distant galaxies recede beyond the point where their light can ever reach us again. Get the Hubble constant wrong, and you get everything downstream of it wrong. So you would think we would know what it is by now. We do not. There are two main ways to measure the Hubble constant. The first is direct. You find objects whose distances you can measure independently, then you measure how fast they are moving away from us by measuring the redshift of their light. Divide the velocity by the distance and you get the Hubble constant. Simple in principle, ferociously difficult in practice. The challenge is measuring distances. Velocity is easy. You point a spectrograph at a galaxy, measure how much its light has been shifted toward the red end of the spectrum, and convert that shift into a recession speed. The redshift tells you directly how fast the galaxy is moving away, but distance is harder. You cannot just point a telescope at a distant galaxy and read off how far away it is. You need a ruler. Astronomers call these rulers standard candles, objects whose true brightness is known. If you know how bright something truly is and you measure how bright it appears from Earth, you can calculate the distance. The apparent brightness falls off with the square of the distance. An object twice as far away appears 4 times dimmer. An object 10 times farther appears 100 times dimmer. Measure the dimming and you have the distance. The trick is finding objects whose true brightness you can trust. The gold standard for nearby distances is a type of star called a Cepheid variable. Cepheids are massive stars that pulsate, brightening and dimming in a regular cycle. The period of the pulsation, how long it takes to go from bright to dim and back to bright again, is directly related to the star's intrinsic luminosity. Longer period, more luminous star; shorter period, less luminous. The relationship is tight and well calibrated. Measure the period and you know the true brightness. Measure the apparent brightness and you have the distance. Cepheids are bright enough to be seen in nearby galaxies, out to distances of about 100 million light-years with the Hubble Space Telescope and farther with the James Webb Space Telescope. Edwin Hubble himself used Cepheids to measure the distances to galaxies in the 1920s. They are the first rung on what astronomers call the cosmic distance ladder. The second rung is Type 1a supernovae. These are exploding stars, specifically white dwarfs, that have accreted enough matter from a companion star to push them over a critical mass threshold of about 1.4 times the mass of our Sun. When a white dwarf crosses that line, it collapses and detonates in a runaway thermonuclear explosion. Because every Type 1a supernova detonates at roughly the same mass, every Type 1a supernova reaches roughly the same peak brightness. They are standard candles, and they are extraordinarily bright, bright enough to be seen across billions of light-years. You cannot use them to measure nearby distances because they are rare. You might see one per galaxy per few centuries, but for distant galaxies they are perfect. Find a Type 1a supernova in a distant galaxy, measure its apparent brightness, compare it to the known true brightness, and you have the distance. The trick is calibrating the supernovae. You need to know their true brightness. To do that, you find supernovae in galaxies that also contain Cepheids. The Cepheids give you the distance to the galaxy. The supernova's apparent brightness, combined with that distance, gives you its true brightness. Once you have calibrated the supernovae using nearby galaxies, you can use them to measure distances to much more distant galaxies where Cepheids are too faint to see. This is how you build the distance ladder. Cepheids measure nearby distances. Supernovae, calibrated with Cepheids, measure farther distances. Combine the distances with the redshifts, and you get the Hubble constant. The team that has done more than anyone else to refine this measurement is called SH0ES, which stands for supernova H0 for the equation of state. H0 is the symbol for the Hubble constant. The SH0ES team is led by Adam Rees, a physicist at Johns Hopkins University who shared the Nobel Prize in 2011 for the discovery that the universe is accelerating. Rees and his colleagues have spent years measuring Cepheids and supernovae using the Hubble Space Telescope and, more recently, the James Webb Space Telescope. Webb's infrared instruments can see Cepheids more clearly than Hubble because infrared light cuts through the dust that often surrounds these stars. That means fewer systematic errors, cleaner measurements, tighter constraints. As of 2024, the SH0ES team's best measurement of the Hubble constant is 73.04 kilometers per second per megaparsec, with an uncertainty of about 1.04, call it 73, give or take 1. That is the direct measurement, the local measurement, the one based on observing objects in the nearby universe and working backward to figure out how fast space is expanding. The second method is indirect. Instead of measuring distances to objects in the nearby universe, you look at the early universe and work forward. The key data source is the cosmic microwave background, the faint glow of radiation left over from the Big Bang. The CMB was emitted roughly 380,000 years after the universe began, at the moment when the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was a hot plasma where photons were constantly scattering off free electrons. After that moment, the photons were free to travel in straight lines. The CMB is a snapshot of the universe at that instant, a baby picture taken when the cosmos was less than 400,000 years old. The European Space Agency's Planck satellite spent about 4.5 years mapping the CMB with extraordinary precision, measuring its temperature in every direction across the sky. The CMB is incredibly uniform. The temperature varies by only about 1 part in 100,000 from place to place, but those tiny variations are everything. They encode information about the density, composition, and geometry of the early universe. By analyzing the pattern of temperature fluctuations, cosmologists can extract the fundamental parameters that describe how the universe behaves. One of those parameters is the Hubble constant. The process is not straightforward. You do not just look at the CMB and read off the expansion rate. You fit the data to a model. The standard model of cosmology is called lambda CDM, where lambda stands for the cosmological constant, dark energy, and CDM stands for cold dark matter. Lambda CDM is a set of equations that describes how the universe evolves from the Big Bang to the present. It includes parameters for the density of ordinary matter, the density of dark matter, the density of dark energy, the rate of expansion, and several other quantities. You plug in values for those parameters, run the equations forward from the early universe to the present, and see whether the predictions match observations. By comparing the predicted pattern of CMB fluctuations to the actual pattern measured by Planck, cosmologists can determine which set of parameters fits best. One of those parameters is the Hubble constant. The Planck team's best fit value is 67.4 kilometers per second per megaparsec, with an uncertainty of about 0.5. Call it 67, give or take 0.5%. That is the indirect measurement, the early universe measurement, the one based on observing the CMB and using the standard model to predict how fast the universe should be expanding today. 67 and 73 do not agree. The gap is about 6 kilometers per second per megaparsec. That might sound small. It is not. In a field where measurements are routinely precise to within 1 or 2%, a 9% discrepancy is enormous, and it is not going away. The uncertainties on both measurements have gotten smaller as the data have improved, but the gap between them has stayed the same or gotten slightly larger. The direct measurement says the universe is expanding at 73. The indirect measurement says it should be expanding at 67. Both teams have checked their work. Both have refined their methods. Both have ruled out the most obvious sources of error, and both are confident their numbers are correct. One of them has to be wrong, or both of them are right, and something else is broken. The statistical significance of the discrepancy is now high enough that physicists have stopped calling it a tension and started calling it a crisis. Significance is measured in sigma, the number of standard deviations separating two measurements. 1 sigma is a small disagreement, the kind that could easily be a fluke. 3 sigma is suggestive. 5 sigma is the threshold for claiming a discovery in particle physics. It means the probability that the disagreement is due to random chance is less than 1 in 3.5 million. The Hubble tension is now at 5 sigma or higher, depending on which datasets you include. Some studies put it at 8 sigma when certain systematic errors are excluded. That is not a fluke, that is a signal. Either the measurements are wrong in ways no one has figured out yet, or the standard model of cosmology is missing something fundamental. For years, the leading suspect was systematic error in the Cepheid measurements. Cepheids live in the crowded, dusty regions of galaxies where new stars are forming. When you point a telescope at one of these regions, the light from the Cepheid can get blended with light from nearby stars. That makes the Cepheid appear brighter than it truly is. Brighter Cepheids mean shorter calculated distances. Shorter distances mean a higher Hubble constant. If the blending was systematic, if it was affecting all the Cepheid measurements in the same way, it could explain the tension. The SH0ES team would be overestimating how fast the universe is expanding because they were underestimating the distances to the galaxies containing the supernovae they were using to calibrate the distance ladder. This was a plausible explanation. It made sense, it was testable, and it turned out to be wrong. The James Webb Space Telescope was designed in part to address this exact problem. Webb's infrared cameras have much sharper vision than Hubble. They can resolve individual stars in crowded regions where Hubble's images showed only blurred blobs of light. If blending was the issue, Webb would see it. The Cepheids would appear dimmer when observed with Webb because the contaminating light from nearby stars would be separated out. The distances would increase, and the Hubble constant would drop back towards 67. Crisis averted. Adam Rees pointed Webb at the same galaxies the SH0ES team had been studying with Hubble. Webb measured the same Cepheids Hubble had measured, and the results were nearly identical. The Cepheids looked the same, the distances held, the Hubble constant stayed at 73. In 2022, Rees and his team published a paper ruling out blending as the cause of the tension at 8 sigma significance. 8 sigma, that is a 1 in 10 to the 15th chance of being wrong, 1 in a quadrillion. Blending was not the problem. The Cepheids were fine. The distances were fine. The tension remained. Other potential sources of error have been examined and ruled out. Dust in the galaxies could dim the Cepheids and supernovae, making them appear farther away than they truly are. But dust affects blue light more than red light, and infrared observations, which are less affected by dust, show the same pattern. The supernovae themselves could be the problem. Maybe distant supernovae are intrinsically fainter than nearby ones, for reasons no one understands. But as more supernovae have been measured across a wider range of distances and galaxy types, the pattern has held. The supernovae are consistent. The redshifts are consistent, the distances are consistent, the Hubble constant is 73, and yet the CMB says it should be 67. So if the measurements are not wrong, what is? The most conservative explanation is that there is some systematic error no one has thought of yet. Something subtle, something that affects one measurement but not the other. This is still possible. Science is full of examples where a systematic error went unnoticed for years until someone finally figured it out. But at this point, both teams have been looking for systematic errors for more than a decade. They have checked everything they can think of. The fact that the tension has survived this long is itself evidence that it is not just a mistake. The more interesting possibility is that the standard model is wrong, not completely wrong. Lambda CDM works too well in too many contexts to be fundamentally broken. It explains the CMB in extraordinary detail. It explains the large-scale structure of the universe, the distribution of galaxies and galaxy clusters across billions of light-years. It explains the relative abundances of hydrogen, helium and lithium produced in the first few minutes after the Big Bang. It gets almost everything right, but maybe it is missing something. Some small piece of physics that was not important in the early universe, but became important later. Something that would change the expansion rate between the time the CMB was emitted and now, without breaking all the other things Lambda CDM explains. One idea that has gained traction is called early dark energy. In this model, there was a brief period in the early universe, sometime before the CMB was emitted, when a form of dark energy different from the cosmological constant briefly dominated the expansion. This early dark energy would have caused the universe to expand slightly faster than Lambda CDM predicts during that period. Then it would have decayed, leaving behind the cosmological constant we see today. The effect of this would be subtle but measurable. It would change the size of the sound horizon, a characteristic scale imprinted in the CMB that depends on how far sound waves could travel through the primordial plasma before the universe became transparent. A smaller sound horizon would mean the features in the CMB are slightly closer together than Lambda CDM predicts. That would change the inferred expansion rate in a way that could reconcile the Planck measurement with the SH0 measurement. Early dark energy is speculative. There is no direct evidence for it, but it is one of the few ideas that can resolve the tension without completely rewriting cosmology. Another possibility is that the universe is not expanding uniformly. Maybe the Milky Way sits in a region of space that is slightly underdense, a local void where there is less matter than average. In an underdense region, the expansion rate would be slightly higher than the cosmic average because there is less gravity pulling inward. If we are sitting in such a region, the direct measurements of the Hubble constant would be biased high. We would be measuring a local expansion rate that does not match the global expansion rate measured by the CMB. This idea has been explored and is still on the table, but it faces challenges. The void would have to be enormous, spanning hundreds of millions of light-years, and it would have to be just the right underdensity to explain the discrepancy without producing other observable effects that we have not seen. Some studies have looked for evidence of such a void and found none. Others have found weak hints that are not conclusive. The jury is still out. A third possibility is more radical. Maybe general relativity, the theory that describes gravity, needs to be modified. General relativity has been tested to extraordinary precision on scales ranging from the solar system to binary pulsars to merging black holes. It works. But all of those tests are at relatively small scales or involve relatively strong gravitational fields. The expansion of the universe is governed by gravity on the largest scales, where the fields are weak and the dynamics are different. Some physicists have proposed that gravity behaves differently on cosmological scales than it does on smaller scales. Modified gravity theories can change the expansion history of the universe in ways that could resolve the Hubble tension. The problem is that most modified gravity theories predict other effects that we have not seen. They change the way galaxies cluster, or the way gravitational lensing works, or the way gravitational waves propagate. So far, no modified gravity theory has been able to resolve the Hubble tension without breaking something else. The tension has become so serious that it is now one of the top priorities in cosmology. New missions and surveys are being designed specifically to measure the Hubble constant with independent methods that do not rely on CFIDs or the CMB. One approach uses gravitational lensing. When light from a distant quasar is bent by the gravity of a foreground galaxy, the light takes multiple paths around the galaxy, and each path has a slightly different length. If the quasar's brightness varies over time, the variations will appear in each lensed image at slightly different times because the light traveled different distances. By measuring the time delays between the images and modeling the gravitational lens, you can calculate the distances involved and extract the Hubble constant. This method is completely independent of the distance ladder. It does not use sepithids or supernovae. It does not rely on the CMB. And it gives a result that is closer to 73 than 67. The tension persists. Another approach uses gravitational waves. When two black holes or neutron stars merge, they emit gravitational waves that carry information about the masses and distances of the merging objects. If the merger also produces light, an electromagnetic counterpart, you can measure the redshift of the host galaxy and combine that with the distance inferred from the gravitational waves to calculate the Hubble constant. This method has been used for a handful of events detected by LIGO and Virgo, the gravitational wave observatories. The uncertainties are still large because the detectors are not yet sensitive enough to measure distances with high precision, but as more events are detected, the method will improve. Early results are consistent with the SH0 measurement. 73, not 67. The Dark Energy Spectroscopic Instrument, or DESI, is a massive survey that started collecting data in 2021. DESI uses a telescope in Arizona equipped with 5,000 fiber optic cables to measure the redshifts of millions of galaxies. The goal is to map the large-scale structure of the universe in 3 dimensions and use that map to measure how the expansion rate has changed over time. In 2023 and 24, the DESI collaboration released its first results. They constrained the Hubble constant using a method called baryon acoustic oscillations, which measures the clustering of galaxies on large scales. The baryon acoustic oscillation scale is a standard ruler imprinted in the distribution of galaxies by sound waves in the early universe, similar to the features in the CMB. DESI's measurement was consistent with the Planck result, 67, not 73. The DESI team explicitly stated that they found no evidence for new physics or a higher Hubble constant. Their data fit the standard lambda CDM model. The tension remained unresolved. What makes this so frustrating is that the tension only gets worse as the data improve. In the early 2010s, when the discrepancy was first noticed, the uncertainties were large enough that the two measurements overlapped within their error bars. You could argue it was just noise. But as Hubble observed more Cepheids and Planck refined its measurements of the CMB, the error bars shrank and the gap stayed the same. The measurements became more precise, but they did not converge. By 2020, the significance had crossed 5 sigma. By 2022, it was approaching 8 sigma for some analyses. The more carefully we measure the expansion rate, the more obvious it becomes that something is wrong. We are not converging on a single answer. We are converging on 2 different answers. Adam Rees has been blunt about what this means. In a 2023 article in Scientific American, he said the Hubble tension is becoming a real crisis for modern cosmology. The word crisis is not hyperbole. It is an acknowledgement that the foundation of our understanding of the universe has a crack in it. Lambda CDM is the best model we have. It explains more observations with fewer free parameters than any competing model. It has been the standard framework for cosmology since the late 1990s, and it is failing a basic test. It cannot simultaneously explain the expansion rate measured in the nearby universe and the expansion rate inferred from the early universe. One of those measurements is wrong, or the model is incomplete, or both. The implications are profound. If the Hubble constant is really 73, the universe is younger than the Planck data suggests. Instead of 13.8 billion years old, it would be closer to 12.5 billion years old. That changes the timeline for everything. The first stars would have formed earlier relative to the age of the universe. Galaxies would have had less time to assemble. Some of the oldest stars we observe, stars that appear to be nearly as old as the universe itself, would suddenly be older than the universe, which is impossible. Something would have to give. If the Hubble constant is really 67, then the direct measurements are systematically wrong in some way no one has been able to identify, despite a decade of scrutiny. That is possible, but it is hard to believe at this point. The SH0ES team has checked everything. They have used multiple independent methods. They have cross-checked their results with gravitational lensing and gravitational waves. The measurement is robust. The third option is that both measurements are correct and the universe is more complicated than lambda CDM allows. Maybe the expansion rate was different in the past. Maybe dark energy is not a cosmological constant. Maybe it has evolved over time in ways that the standard model does not account for. Maybe there is a new field, a new particle, a new force that was important in the early universe and has since faded or changed. Maybe the universe is not homogeneous on the scales we thought it was. Maybe gravity works differently than we think. Any of these possibilities would require new physics. They would require adding something to the standard model or modifying something fundamental about how we think the universe behaves. That is exciting if you are a theorist looking for new ideas to explore. It is terrifying if you are a cosmologist who spent the last 30 years building a model that seemed to work and now has to face the possibility that it does not. The Hubble tension is not the only problem lambda CDM is facing, but it is the most glaring one. It is a straightforward measurement. Measure distances, measure velocities, divide one by the other. Two different teams using two completely independent methods should get the same answer. They do not. And after more than a decade of trying, no one has been able to make the discrepancy go away. The universe, it seems, is not interested in making things easy. It keeps handing us data that do not fit, and the more precisely we measure, the more obvious it becomes that the model we have been using is missing something. We just do not know what. The resolution, when it comes, will not be subtle. Either one of the measurements will turn out to have a flaw that everyone missed, which at this point seems unlikely, or the standard model of cosmology will need to be revised in a fundamental way. New physics will have to be added. New forces, new fields, new particles, something that changes the expansion history of the universe without breaking the hundreds of other observations that lambda CDM explains. That is a tall order, but the alternative is to keep pretending the tension does not exist, and that is no longer an option. The gap is too large, the significance is too high, the crisis is real, and it is about to get stranger. Because the Hubble tension is not the only way the universe is misbehaving. There is something else out there, something pulling on our galaxy and every galaxy within hundreds of millions of light years. Something massive, something hidden, something we have been drifting toward for billions of years, and no one knows what it is. And it is about to get stranger, because the Hubble tension is not the only way the universe is misbehaving. There is something else out there, something pulling on our galaxy and every galaxy within hundreds of millions of light years. Something massive, something hidden, something we have been drifting toward for billions of years, and no one knows what it is. The Milky Way is not sitting still. This might sound obvious. Nothing in the universe sits still. The Earth orbits the Sun at 30 kilometers per second. The Sun orbits the center of the Milky Way at roughly 220 kilometers per second. The Milky Way itself is moving, not just spinning in place, but traveling through space, headed somewhere. And for a long time, astronomers assumed that motion was simple. The galaxy was coasting, drifting along with the general expansion of the universe, nudged slightly by the gravity of nearby galaxies, but otherwise following a predictable path. That assumption turned out to be completely wrong. The Milky Way is not coasting. It is being pulled, hard, in a specific direction, towards something so massive that it is dragging our entire galaxy, along with thousands of other galaxies spanning hundreds of millions of light years, toward a point in space we cannot see. Astronomers call it the Great Attractor, and despite decades of searching, we still do not know exactly what it is. The story starts with a puzzle that emerged in the 1970s. Astronomers had spent decades measuring the redshifts of galaxies, cataloging how fast they were moving away from us as the universe expanded. Edwin Hubble had discovered in the 1920s that the universe was expanding, and by the mid-20th century, astronomers had refined that discovery into a detailed picture of how galaxies move. Most galaxies are receding from us. The farther away they are, the faster they recede. This is the Hubble flow, the smooth, predictable expansion of space carrying galaxies apart. But the Hubble flow is not the only motion galaxies have. They also have what astronomers call peculiar velocities, motions that are not due to the expansion of the universe but are instead caused by the gravitational pull of nearby massive objects. A galaxy sitting next to a large cluster will be pulled toward that cluster. Its peculiar velocity will add to or subtract from the Hubble flow, making it move slightly faster or slower than the expansion alone would predict. Peculiar velocities are usually small, a few hundred kilometers per second at most, and they are local. They reflect the influence of nearby structures. They should average out to zero when you look at large enough volumes of space. If you measure the peculiar velocities of 1,000 galaxies scattered across 1 billion light years, some will be moving toward you, some away, and the average should be close to zero because the universe, on large scales, is expanding uniformly in all directions. Except that is not what astronomers found. In 1973, a team of astronomers noticed something odd. Galaxies in our local region of the universe were not moving randomly. They were all drifting in the same direction. Not slowly, fast, several hundred kilometers per second. This was not a local effect. It was not just the Milky Way and Andromeda tugging on each other. It was a large-scale bulk flow, a coherent motion of galaxies spanning tens of millions of light years, all moving together as if they were being pulled by something enormous. The motion was in the direction of the constellations Hydra and Centaurus, a region of the southern sky that sits low on the horizon for observers in the northern hemisphere and is largely obscured by the plane of the Milky Way. The pull was strong enough to give the Milky Way a peculiar velocity of around 600 kilometers per second. 600. That is more than twice as fast as the Sun orbits the galactic center. The entire galaxy, along with thousands of others, was hurtling through space towards something unseen. At first, no one believed it. The measurements were difficult. Peculiar velocities are hard to calculate because you have to measure both the redshift of a galaxy, which tells you how fast it is moving away due to the expansion of the universe, and its true distance, which tells you how fast it should be moving if it were just following the Hubble flow. The difference between those two numbers is the peculiar velocity, but measuring distances is tricky. If you get the distance wrong, you get the peculiar velocity wrong. For years, the bulk flow was dismissed as a measurement artifact, a mistake caused by errors in the distance estimates. But as more data came in, the pattern held. Different teams using different methods kept finding the same thing. Galaxies in our local region were moving together in a specific direction. By the mid-1980s, the evidence was strong enough that astronomers had to take it seriously. Something was pulling on us, something big. In 1986, a team of astronomers led by Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Telovich and Gary Wegner, collectively known as the Seven Samurai, published a paper that changed the conversation.
They had measured the distances and velocities of about 400 galaxies in the nearby universe using a technique called the Tully-Fisher relation, which relates the rotation speed of a spiral galaxy to its intrinsic brightness. Measure how fast a galaxy is spinning and you know how bright it should be. Measure how bright it appears and you have the distance.
The Seven Samurai used this method to map the peculiar velocities of galaxies across a volume spanning hundreds of millions of light-years. The results were unambiguous. The galaxies were not moving randomly. They were streaming toward a specific point in space, a region located roughly 150 to 250 million light-years away in the direction of the southern constellations Norma and Triangulum Australe. Dressler called it the Great Attractor. The name stuck. The Great Attractor was not a galaxy. It was not a cluster of galaxies. It was something larger, something more diffuse, a concentration of mass so enormous that it was pulling on structures across hundreds of millions of light-years. The mass estimates were staggering. To produce the observed bulk flow, the Great Attractor would need to contain tens of thousands of times the mass of the Milky Way, that is tens of quadrillions of solar masses, a number so large it barely fits in the mind. And it was sitting in one of the most frustrating places in the sky. The region toward the Great Attractor lies behind the plane of the Milky Way, buried in what astronomers call the zone of avoidance. This is the band of sky where the disk of our own galaxy blocks the view. The Milky Way is full of dust, gas and stars. When you look through the plane of the galaxy, you are looking through all that material, and it obscures everything behind it. Light from distant galaxies gets absorbed by dust or scattered by gas. The farther you look, the worse it gets. For decades, the zone of avoidance was a blank spot in our maps of the universe. We knew there were galaxies back there, we just could not see them. The Great Attractor was hidden in that blank spot. Astronomers could infer its existence from the motions of galaxies around it, the same way you can infer the presence of a planet by watching how it tugs on the stars nearby. But they could not see the Great Attractor itself. It was like trying to study a black hole by watching how stars orbit around it. You know something is there because of what it does to everything else. But the thing itself remains invisible. For years, the Great Attractor was a ghost, a gravitational anomaly inferred from indirect evidence, a point in space toward which everything in our corner of the universe was falling, and we could not see what was pulling us. The breakthrough came in the 1990s with new telescopes and new techniques for peering through the dust. Infrared light, which has longer wavelengths than visible light, can pass through dust more easily. X-ray observations can detect hot gas in galaxy clusters, which glows brightly in X-rays regardless of how much dust is in the way. Radio telescopes can map the distribution of neutral hydrogen gas, which emits a characteristic signal at 21 centimeters wavelength that cuts through the obscuration. By combining observations at multiple wavelengths, astronomers started to build a picture of what was hiding in the zone of avoidance. What they found was not a single massive object. It was a complex, tangled web of galaxy clusters, filaments, and dark matter halos, all concentrated in a region centered on a structure called the Norma cluster. The Norma cluster is enormous. It contains roughly 1,000 trillion solar masses, 1,000 times the mass of the Milky Way, packed into a region a few million light-years across. It sits almost exactly where the models predicted the Great Attractor should be. But the Norma cluster, as massive as it is not enough. The mass of the cluster alone cannot account for the strength of the pull we are feeling. The Great Attractor is not just the Norma cluster. It is the Norma cluster plus everything around it. A supercluster, a vast gravitationally bound structure made up of multiple galaxy clusters connected by filaments of galaxies and dark matter. The visible galaxies are just the tip of the iceberg. Most of the mass is dark matter, invisible halos surrounding and permeating the entire structure. Mapping the Great Attractor in detail required a monumental effort. Astronomers used the Hubble Space Telescope to observe galaxies in the zone of avoidance, picking out individual objects through gaps in the dust. They used redshift surveys, massive projects that measure the distances to thousands of galaxies by analyzing the spectra of their light, to map the three-dimensional distribution of matter in the region. One of the most ambitious surveys was the 2-degree field galaxy redshift survey, or 2DF, which measured redshifts for more than 200,000 galaxies. Another was the Sloan Digital Sky Survey, which eventually catalogued millions. These surveys revealed that the Great Attractor is part of a much larger structure. It is not the biggest thing in the universe. It is not even the biggest thing nearby. It is the gravitational center of a supercluster of superclusters, a structure so large that it took decades to fully map. In 2014, a team led by astronomer Brent Tully published a paper that finally put the Great Attractor into context. Using data from redshift surveys and peculiar velocity measurements, Tully and his colleagues mapped the gravitational flow of galaxies across a volume spanning 500 million light-years. They traced the paths of galaxies as they moved through space, following the invisible currents of gravity that shaped their motion. What they found was that the Milky Way, along with hundreds of thousands of other galaxies, is part of a vast supercluster that Tully named Laniakea. The name is Hawaiian, meaning immense heaven, and it fits. Laniakea is one of the largest structures in the observable universe. It contains roughly 100,000 large galaxies and has a total mass of about 100 quadrillion suns. The Great Attractor is the gravitational core of Laniakea. It is the point toward which all the galaxies in the supercluster are flowing, the bottom of the basin where everything eventually ends up. Laniakea is not a single object, it is a web. Imagine a spider web stretched across hundreds of millions of light-years, with thick strands of galaxies running between massive clusters. The clusters sit at the intersections, the nodes where multiple strands meet. The Great Attractor is one of the largest nodes, a dense concentration of mass where multiple filaments converge. The Milky Way sits on the outskirts of Laniakea, in a relatively underdense region near the edge. We are not at the center. We are in the suburbs, drifting slowly inward along one of the filaments, pulled by the combined gravity of everything toward the core. At our current speed of 600 kilometers per second, it would take us roughly 20 billion years to reach the Great Attractor. But we will never get there. The universe is expanding. The space between us and the Great Attractor is growing, and that expansion is accelerating thanks to dark energy. The pull of the Great Attractor is strong, but it is not strong enough to overcome the expansion. We are falling toward it, but the finish line is moving away from us faster than we are falling. In a few billion years, the expansion will have carried the Great Attractor so far away that its gravity will no longer have any measurable effect on us. We will stop falling and start drifting. The pull will fade, and the Great Attractor will recede into the distance, eventually crossing the cosmic horizon and disappearing from view forever. But for now, we are still falling. Every second, the Milky Way moves roughly 600 kilometers closer to the Great Attractor. You are moving with it. The chair you are sitting in, the building you are in, the planet beneath your feet, the entire solar system, the entire galaxy, all of it is being pulled toward a point in space hidden behind a veil of dust and stars. You cannot see it, you cannot feel it, but it is happening right now. And it has been happening for billions of years. The Great Attractor has been pulling on the Milky Way since long before the Sun formed, since long before the Earth existed, since before life began. It is one of the oldest forces shaping our corner of the universe, and we only discovered it 40 years ago. The Great Attractor is not unique. It is not the only massive concentration of galaxies in the universe. It is not even the only one nearby. About 650 million light-years away, in the direction of the constellation Centaurus, there is an even larger structure called the Shapley supercluster. Shapley is the biggest concentration of galaxies in the local universe. It contains more than 8,000 large galaxies and has a total mass several times greater than Laniakea. And here is the thing. The Great Attractor is falling toward Shapley. Laniakea, the entire supercluster, is being pulled in that direction. The Milky Way is falling toward the Great Attractor. The Great Attractor is falling toward Shapley. And Shapley is probably falling toward something even larger that we have not mapped yet. The universe is not static. It is not a collection of objects sitting still in space. It is a dynamic, flowing system where everything is falling toward everything else, pulled by gravity into ever larger structures. The galaxies are not scattered randomly, they are organized into a hierarchy. Small galaxies fall into larger galaxies. Groups of galaxies fall into clusters. Clusters fall into superclusters. Superclusters fall toward even larger concentrations. The entire universe is a web of flows, currents of matter streaming through space along invisible channels carved by gravity and dark matter. The discovery of the Great Attractor changed the way astronomers think about large-scale structure. Before the 1980s, the assumption was that the universe was roughly uniform on large scales. Galaxies were clustered, yes, but the clusters were distributed more or less evenly. The universe was lumpy, but the lumps were small and local. The Great Attractor proved that assumption wrong. The universe is not uniform. It is organized into enormous structures that span hundreds of millions of light-years. Those structures are not random. They are shaped by gravity, which amplifies tiny density fluctuations left over from the Big Bang into the vast cosmic web we see today. The Great Attractor is a node in that web, a place where matter has concentrated, a place where gravity is stronger than average, a place where everything nearby is falling inward. The fact that we are falling toward the Great Attractor tells us something important about the universe. It tells us that gravity is still the dominant force shaping the motion of galaxies on scales of a few 100 million light-years. Dark energy is pushing the universe apart on larger scales, accelerating the expansion, but on smaller scales, gravity still wins. Galaxies within superclusters are still falling toward each other. The web is still growing denser at the nodes. The Great Attractor is still attracting, but this will not last. Over the next tens of billions of years, dark energy will take over completely. The superclusters will stop growing. The filaments will stretch and thin. The clusters will drift apart. Eventually, Laniakea will dissolve. The Great Attractor will fade into the distance. The Milky Way will be alone, or nearly alone, surrounded by a handful of galaxies that were close enough to remain gravitationally bound. Everything else will have receded beyond the horizon, carried away by the accelerating expansion. The web will break, the flows will stop, and the universe will enter a new phase, one where gravity no longer shapes the large-scale structure because there is no longer any large-scale structure left to shape. But that is billions of years away. For now, the Great Attractor is real. It is pulling, and we are falling. At 600 kilometers per second, the Milky Way is racing toward a point in space that we can barely see, drawn by a concentration of mass so large that it bends the trajectories of galaxies across 250 million light-years. The Great Attractor is not a monster, it is not a threat. It is just gravity doing what gravity does, pulling matter together, shaping the universe one galaxy at a time. But it is a reminder of how little we understand about the cosmos we live in. For decades, astronomers assumed the Milky Way was drifting peacefully through space. It was not. It was falling. And no one noticed until someone thought to ask the question, where are we going? The answer to that question turned out to be more complicated than anyone expected. The Great Attractor is not a single object. It is a region, a point in space where the gravitational potential reaches a minimum, where the pull is strongest, where everything nearby is flowing inward. It is the center of mass of a supercluster, the balance point around which hundreds of thousands of galaxies orbit and fall. And it is mostly invisible. The galaxies we can see are just markers, breadcrumbs showing us where the mass is concentrated. Most of the mass is dark matter, the same invisible substance that holds galaxies together and outweighs ordinary matter by a factor of 5. The Great Attractor is made mostly of dark matter. The galaxies are just the visible traces, the foam on the surface of a much deeper ocean. This is the universe we live in, not a static backdrop of stars and galaxies arranged like points of light on a velvet curtain, but a dynamic, flowing system where everything is in motion, pulled by invisible forces toward destinations we can barely see. The Milky Way is not floating in space, it is falling. Falling toward the Great Attractor, which is falling toward the Shapley supercluster, which is falling toward something else we have not discovered yet. The universe is a cascade of motion, a hierarchy of falls within falls, each one shaped by gravity, each one pulling matter together into larger and larger structures, and the structures themselves are not isolated, they are connected. Filaments of galaxies stretch between the clusters, linking them into a web that spans billions of light-years. The Great Attractor is one node in that web. Shapley is another. The Milky Way is a tiny speck drifting along one of the threads, caught in the flow, pulled toward the center. The discovery of the Great Attractor was not an accident. It was the result of careful, patient observation, of astronomers asking the right questions and being willing to follow the evidence even when it led somewhere unexpected. For decades, the assumption was that the universe was simple. Galaxies were expanding apart. The motion was smooth and predictable. The Great Attractor proved that assumption wrong. The universe is more complicated than anyone thought. The flows are real, the pulls are real, and the structures shaping those flows are larger than anything we imagined. The Great Attractor is not the end of the story. It is the beginning. It is the first hint of a larger pattern, a cosmic web of filaments and voids that stretches across the entire observable universe. And that web, that vast, intricate structure of matter and dark matter, is the subject of the next part of this story, because the Great Attractor is not alone. It is part of something much, much bigger. Because the Great Attractor is not alone, It is part of something much, much bigger, something that makes superclusters look like dots on a map, something so vast that when astronomers first started to see it, they did not believe it could be real. The universe is not a random scattering of galaxies. It is not a smooth, uniform distribution of matter stretching in all directions. It is organized, structured, woven into a pattern so intricate and so enormous that it took decades of mapping and millions of galaxy measurements to even begin to see it. And once you see it, you cannot unsee it. The universe has a skeleton, a framework, a web. Astronomers call it the cosmic web, and the name is not a metaphor, it is an accurate description. The large-scale structure of the universe looks like a three-dimensional spiderweb stretching across billions of light-years in every direction. Thick strands of galaxies and dark matter, filaments hundreds of millions of light-years long, connect dense nodes where galaxy clusters sit. Between the filaments are voids, vast empty regions where almost nothing exists. The voids are enormous. Some of them are more than 1 billion light-years across. If you were standing in the middle of one, you could look in every direction and see nothing. No galaxies, no stars, just darkness. The galaxies are not distributed evenly. They are concentrated along the filaments, strung out like beads on a wire, flowing along invisible channels carved by gravity. The web is not static, it is growing. The filaments are getting denser, the voids are getting emptier, and the whole structure is expanding, carried along by the accelerating expansion of space itself. This is the universe at its largest scale, not individual galaxies, not clusters, not even superclusters. The cosmic web is the biggest structure there is. It spans the entire observable universe, roughly 90 billion light-years from edge to edge, and it is almost entirely invisible. The galaxies we can see are just markers, tiny glowing specks showing us where the filaments are. Most of the web is dark matter. The same invisible substance that holds galaxies together outweighs ordinary matter by a factor of 5 and makes up 85% of the cosmic web's total mass. The dark matter forms the scaffolding. The galaxies just light it up. You cannot see the web directly. You can only see where the galaxies are, and from that you infer where the dark matter must be. It is like looking at a city at night from space. You see the lights, and from the pattern of lights you can infer the roads, the highways, the intersections, the empty spaces in between. The lights are not the city. They just show you where the city is. The galaxies are not the web. They just show you where the web is. The discovery of the cosmic web did not happen all at once. It emerged gradually over the course of several decades as astronomers built bigger telescopes, measured more galaxies, and mapped the universe in ever greater detail. The first hints came in the 1970s and 1980s when redshift surveys started to reveal that galaxies were not distributed randomly. They were clustered in specific patterns. In 1989, a team led by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics published a map of galaxies in a thin slice of the sky. The map showed something stunning. The galaxies were arranged in long, thin structures, separated by large, empty regions. One of the structures was so prominent that Geller and Huchra called it the Great Wall. It was a sheet of galaxies stretching across more than 500 million light-years, one of the largest structures ever observed at the time. The Great Wall was not a single object. It was a superposition of multiple filaments and clusters, aligned in a way that made them appear as a continuous wall when viewed from our perspective. But it was real. The galaxies were there, all moving together, all part of the same structure. And it was massive. The Great Wall contains tens of thousands of galaxies and has a total mass of about 10 quadrillion suns. And it was just one piece of a much larger pattern. As more galaxies were measured, the pattern became clearer. In the 1990s and 2000s, massive galaxy surveys like the 2-degree field galaxy redshift survey and the Sloan Digital Sky Survey measured the redshifts of millions of galaxies, building three-dimensional maps of the universe. The Sloan survey alone catalogued more than 1 million galaxies. The maps revealed the cosmic web in stunning detail. Filaments connecting clusters, voids separating the filaments, nodes where multiple filaments converged. The structure was fractal, self-similar at multiple scales. Small filaments fed into larger filaments. Clusters sat at the intersections. Superclusters, like Laniakea, were just the densest regions where many filaments met. The web was everywhere. It filled the entire universe, and it was not a recent development. The web had been there all along. We just had not been able to see it. The cosmic web did not form overnight. It has been growing for nearly 14 billion years, shaped by gravity amplifying tiny density fluctuations left over from the Big Bang. In the earliest moments of the universe, the matter was almost perfectly smooth, almost, but not quite. There were tiny variations in density, regions where the matter was slightly more concentrated than average, and regions where it was slightly less concentrated. These variations were tiny, only about 1 part in 100,000, but they were enough. Gravity amplifies differences. In regions that were slightly denser than average, gravity pulled in more matter, making them even denser. In regions that were slightly less dense, matter flowed outward, making them even emptier. Over time, the dense regions grew denser and the empty regions grew emptier. The universe began to develop structure. The densest regions collapsed into clumps. The clumps merged into larger clumps. The largest clumps became the first galaxies. The galaxies clustered together along the lines where the density was highest, tracing out the filaments. The voids, the regions where the density was lowest, expanded and emptied out as matter flowed away from them into the denser regions. By the time the universe was a few 100 million years old, the basic architecture of the cosmic web was already in place. The filaments, the nodes, the voids, all of it existed. It was faint. The structures were less pronounced than they are today, but the pattern was there, waiting to grow. Modern simulations of cosmic structure formation can reproduce the cosmic web with extraordinary fidelity. The Millennium simulation, run in 2005, simulated the evolution of dark matter across a cube of space more than 2 billion light-years on a side, tracking the motion of more than 10 billion particles from the Big Bang to the present day. The simulation took months to run on some of the most powerful supercomputers in the world. The result was a detailed map of how dark matter, clusters and filaments form over cosmic time. The simulated universe looked like the real universe. Filaments connecting clusters, voids separating the filaments, nodes where multiple filaments converged. The match was so good that astronomers could overlay the simulation onto observational data and see the same structures. The Illustrating simulation, a more recent and even more ambitious project, added baryonic matter, gas and stars to the mix, simulating not just the dark matter, but the galaxies themselves. It tracked how gas flows along the filaments, how it cools and collapses into galaxies, how stars form and explode, how black holes grow and feed. The simulated galaxies formed in the same places as the real galaxies, along the filaments, at the nodes. The simulations confirmed what the observations had been suggesting for decades. The cosmic web is real. It is not an artifact of how we look at the sky. It is the fundamental structure of the universe, and it is shaped by dark matter. Dark matter dominates the formation and evolution of the cosmic web because dark matter does not interact with light or gas. It only interacts through gravity. That makes it simple. Baryonic matter, the ordinary stuff made of atoms, is messy. Gas can heat up and cool down. It can collapse into stars. It can be blown apart by supernovae. It can radiate energy and lose pressure and fall into complicated configurations. Dark matter does none of that. It just drifts. It clumps together under its own gravity, forming halos, and those halos pull in the baryonic matter. The galaxies form where the dark matter is. The filaments trace the dark matter. The voids are where the dark matter is not. The cosmic web is fundamentally a map of dark matter distribution. The galaxies are just markers showing us where the dark matter has concentrated. Observing the cosmic web directly is nearly impossible because most of it is invisible. The dark matter halos that make up the filaments do not emit light. They do not absorb light. They do not reflect light. They are transparent. The only way to detect them is through their gravitational effects. Gravitational lensing can reveal dark matter halos by measuring how they bend the light from more distant galaxies. But lensing works best for very dense structures like galaxy clusters. The filaments are more diffuse. They are still massive, containing billions of times the mass of the Milky Way, but they are spread out over such large volumes that their lensing signals are weak. Detecting them requires exquisitely precise measurements of the shapes and positions of millions of background galaxies. The European Space Agency's Euclid mission, launched in 2023, was designed specifically to do this. Euclid is mapping the shapes of billions of galaxies across more than a third of the sky, measuring how their light has been distorted by the gravitational pull of foreground structures. The goal is to build a three-dimensional map of dark matter distribution across the universe, revealing the cosmic web in unprecedented detail. Early results from Euclid have already shown hints of filaments connecting clusters, faint bridges of dark matter linking the nodes. The web is becoming visible, one pixel at a time. There is another way to observe the cosmic web, and it is more direct. Hidden within the filaments is gas. Not a lot of it, and not very dense, but enough to be detected under the right conditions. The gas is hydrogen, the simplest and most abundant element in the universe, left over from the Big Bang and never incorporated into galaxies. It drifts through the filaments, too diffuse to collapse into stars, but dense enough to absorb light. When light from a distant quasar, one of the brightest objects in the universe, passes through a filament on its way to Earth, the hydrogen gas in the filament absorbs specific wavelengths of that light. The quasar's spectrum, when you look at it through a spectrograph, shows a forest of dark absorption lines, each one marking a place where the light passed through a cloud of hydrogen. Astronomers call these features the Lyman alpha forest, named after the specific wavelength of light that hydrogen absorbs most strongly. By analyzing the pattern of absorption lines in the spectra of many quasars, astronomers can map the distribution of gas along the filaments. The technique is indirect. You are not seeing the gas directly. You are seeing the shadow it casts on the light from something behind it. But it works. The Lyman alpha forest has revealed filaments stretching between galaxies, tracing the same structures that simulations predict. The gas is there, flowing along the dark matter scaffolding, feeding the galaxies at the nodes. The cosmic web is not empty. It is threaded with gas, invisible until something bright enough passes behind it to cast its shadow. In 2025, astronomers using the Meerkat radio telescope in South Africa announced a discovery that shocked the field. They detected a filament that was rotating. Filaments are supposed to be static structures, scaffolding where matter flows inward along the gravitational potential. They are not supposed to spin, but this one was. The filament was about 50 million light-years long and roughly 117,000 light-years wide. a thin thread of galaxies and gas connecting two massive galaxy clusters. The entire structure was rotating at roughly 246,000 miles per hour. The rotation was slow, taking hundreds of millions of years to complete a single turn, but it was unmistakable. The galaxies along the filament were moving in a coherent pattern, all orbiting around the filament's axis. This was the first time anyone had detected rotation in a structure this large. Planets rotate, stars rotate, galaxies rotate, clusters can have some rotational motion. But a filament 50 million light-years long? That was new, and it raised questions. Where did the angular momentum come from? Filaments form from the collapse of initially smooth distributions of matter. The collapse should wash out any rotation, unless the initial conditions were not smooth, unless there was some twist, some asymmetry in the density field that seeded the rotation from the beginning, or unless something else, some large-scale torque from neighboring structures, spun the filament up after it formed. The discovery is still being studied. No one knows yet what it means, but it is a reminder that the cosmic web is not a static backdrop. It is dynamic, it evolves, it moves, and it does things we do not expect. The voids, those vast empty regions between the filaments, are as important to the structure of the cosmic web as the filaments themselves. Voids are not truly empty. They contain some galaxies, but far fewer than the filaments or clusters. A typical void might contain a few dozen small galaxies scattered across a volume a billion light-years wide. For comparison, a similar volume along a filament could contain thousands or tens of thousands of galaxies. The voids are underdense by a factor of 10 or more. They are the largest structures in the universe by volume. The Boots void, one of the first large voids discovered, is roughly 330 million light-years across and contains only about 60 galaxies. If the Milky Way were sitting in the center of the Boots void, the nearest large galaxy would be more than 100 million light-years away. The night sky would be almost empty, a handful of faint smudges visible only through the most powerful telescopes. No Andromeda galaxy, no Magellanic clouds, just darkness. Civilizations that evolved in the center of a void would have a completely different view of the universe. They would not discover that the universe is full of galaxies until they built telescopes powerful enough to see across the void to the filaments beyond. Their cosmology would be delayed by centuries. They would assume the universe was empty because from their perspective it would be. Voids are not passive. They are expanding faster than the average expansion rate of the universe. This is because they are underdense. In regions where there is less matter, there is less gravity pulling inward, which means the expansion of space is less opposed. The voids grow. The matter inside them flows outward to denser filaments, emptying the voids even further. Over time, the voids get larger and emptier. The filaments get denser and more pronounced. The cosmic web becomes more sharply defined. This process will continue for billions of years, driven by the interplay between gravity, which pulls matter together, and dark energy, which pushes space apart. Dark energy is the dominant force on the largest scales. It is accelerating the expansion of the universe, pulling distant structures apart faster than gravity can draw them together. But on smaller scales, scales of a few 100 million light-years or less, gravity still wins. Within a supercluster, galaxies are still falling toward the center. Along a filament, gas is still flowing inward, feeding the galaxies. The cosmic web is still growing, but it will not grow forever. At some point, dark energy will take over completely. The filaments will stop densifying. The flow of matter will stop. The web will freeze in place, its structure preserved as the universe expands around it. Then, over tens of billions of years, the expansion will stretch the web. The filaments will thin. The clusters will drift apart. Eventually, the web will dissolve, and the universe will return to a state of near uniformity, all the structure erased by the relentless pull of dark energy. But that is far in the future. For now, the cosmic web is here, and it is magnificent. The largest known structure in the cosmic web is the Hercules Corona Borealis Great Wall, a vast concentration of galaxy clusters stretching across roughly 10 billion light-years. 10 billion. That is more than 10% of the diameter of the observable universe. The structure is so large that it pushes against the limits of what the standard model of cosmology allows. According to the cosmological principle, the universe should be roughly homogeneous on large scales. Structures larger than about 1.2 billion light-years should not exist because the universe has not had enough time since the Big Bang for gravity to pull matter together over such vast distances. The Hercules Corona Borealis Great Wall is roughly 10 times larger than that limit. It should not exist, and yet it does. The structure was discovered by analyzing the distribution of gamma-ray bursts, the most energetic explosions in the universe, which occur when massive stars collapse into black holes or when neutron stars merge. Gamma-ray bursts are so bright that they can be seen across billions of light-years. By mapping where the bursts occur, astronomers can trace the distribution of galaxies because gamma-ray bursts happen where there are massive stars, and massive stars form in galaxies. The gamma-ray burst data revealed a clustering, a concentration of bursts in a specific region of the sky. Follow-up observations with optical telescopes confirmed that the region contained an unusually high density of galaxies and galaxy clusters. The structure stretched across 10 billion light-years, a wall of matter so vast that it dwarfed every other known structure in the universe. The existence of the Hercules Corona Borealis Great Wall is controversial. Some astronomers argue that it is not a single coherent structure, but a chance alignment of several smaller structures that happen to lie along the same line of sight. Others argue that the statistical significance of the clustering is strong enough to rule out chance. The debate continues. But whether it is one structure or several, the fact remains that there is an enormous concentration of matter in that region of the sky, and it is larger than the cosmological principle says it should be. This is not the only tension between observations and theory. The Sloan Great Wall, another massive structure discovered in the Sloan Digital Sky Survey, stretches across about 1.3 billion light-years and contains tens of thousands of galaxies. The Laniakea supercluster, the structure that contains the Milky Way and the Great Attractor, spans about 520 million light-years. The web is full of structures that are barely allowed by the models. They are not impossible, but they are unlikely. And the fact that we keep finding them suggests that either we are living in an unusually structured region of the universe, which seems unlikely, or the models are missing something. Maybe the initial density fluctuations left over from the Big Bang were not as smooth as we think. Maybe there were larger scale patterns that the models do not account for. Maybe dark matter behaves slightly differently on the largest scales than we assume. Or maybe the cosmological principle, the assumption that the universe is homogeneous on large scales, is not quite right. Maybe the universe is lumpier than we thought. The cosmic web is not just a static map of where galaxies are. It is a dynamic system that shapes how galaxies form and evolve. Galaxies do not form in isolation. They form along the filaments, where gas flows inward, cools, and collapses. The filaments act as highways, channels along which matter travels from the voids to the clusters. A galaxy sitting at the intersection of several filaments at a node in the web has access to a steady supply of gas flowing in from multiple directions. It can grow large. It can form stars continuously. It can merge with other galaxies that are also flowing toward the node. Galaxies in these environments are typically massive, elliptical, old. They have used up most of their gas and stopped forming stars. They are red and dead, sitting at the centers of clusters, surrounded by hundreds or thousands of smaller galaxies. In contrast, a galaxy sitting along a filament, away from the nodes, has access to less gas. It forms stars more slowly. It is more likely to be a spiral galaxy, still actively forming stars, still blue and alive. Galaxies in the voids are the loneliest. They receive almost no gas from the filaments. They form stars very slowly, if at all. They are small, dim, isolated. The cosmic web determines where galaxies form, how fast they grow, and what they look like. It is the environment that shapes everything. The filaments themselves are not just conduits for gas, they are also highways for galaxies. Galaxies do not just sit still, they move along the filaments, flowing toward the nodes, merging with other galaxies along the way. The Milky Way is moving along a filament right now, falling toward the Great Attractor. Andromeda is moving along the same filament, falling in the same direction. In a few billion years, the two galaxies will collide and merge, forming a single larger galaxy. That merger is happening because both galaxies are following the flow of the cosmic web. The web is not just a map, it is a river system, and the galaxies are boats being carried along by the current. The flow is slow, a few hundred kilometers per second, but it is relentless. Over billions of years, the flow reshapes the distribution of galaxies, concentrating them at the nodes, thinning them along the filaments, emptying the voids. The web is a machine that sorts matter, organizing it into patterns that repeat across the entire universe. One of the most remarkable aspects of the cosmic web is how early it formed. Observations with the James Webb Space Telescope have detected filaments and protoclusters at redshifts greater than 10, meaning we are seeing them as they existed less than 500 million years after the Big Bang. At that time, the universe was less than 4% of its current age, and yet the web was already there. The filaments were fainter, the structures less pronounced, but the pattern was recognizable. The nodes were beginning to form. The voids were starting to empty out. The galaxies were clustering along the same lines that would, billions of years later, grow into the massive filaments we see today. This tells us that the seeds of the cosmic web were planted very early in the first moments after the Big Bang. The tiny density fluctuations left over from inflation, the brief period of exponential expansion that occurred in the first fraction of a second, were enough to set the entire structure in motion. Those fluctuations were amplified by gravity over billions of years, growing into the galaxies, clusters, and filaments we see today. The cosmic web is not something that happened recently. It is a feature of the universe that has been growing since the very beginning, and it will keep growing until dark energy tears it apart. The web is a paradox. It is the largest structure in the universe, and yet it is almost entirely invisible. It is everywhere, threading through every cubic meter of space, and yet we only see the tiniest fraction of it. The galaxies are like Christmas lights on a tree. They show you where the branches are, but most of the tree is in shadow. Most of the web is dark matter and empty space. The matter we can see, the stars and galaxies, makes up less than 5% of the total. The rest is hidden. And that hidden majority is what holds the visible universe together. The cosmic web is the skeleton of the cosmos. Without it, there would be no galaxies. Without it, there would be no stars. Without it, there would be no planets, no life, no you. Everything you see when you look up at the night sky exists because of a framework you cannot see. The web is the foundation. The galaxies are just the decoration. And here is the strangest part. The web is being built by one invisible force and torn apart by another. Dark matter builds the web. Its gravity pulls matter together, shaping the filaments, concentrating the clusters, carving out the voids. Dark energy tears the web apart. Its negative pressure pushes space apart, accelerating the expansion, stretching the filaments, emptying the voids even further. For the first 9 billion years of the universe's history, dark matter was winning. The web was growing. The structures were getting denser. The flow of matter along the filaments was strengthening. Then, about 5 billion years ago, dark energy took over. The expansion started accelerating. The distant structures started receding faster than gravity could pull them together. The web stopped growing. It is still here. It is still visible, but it has entered a new phase. The filaments are no longer densifying. The voids are no longer emptying out. The web has reached its maximum extent. From now on, it will only shrink. The structures we see today, the filaments and clusters and superclusters, are the final form of the cosmic web. They will persist for billions of years, but they will not grow larger. They will not become more pronounced. They will slowly, gradually dissolve as the expansion carries them apart. In 100 billion years, the web will be gone. The clusters will have drifted beyond each other's horizons. The filaments will have stretched into invisibility. The voids will have expanded to fill the entire universe. And future observers, if there are any, will look out into the cosmos and see almost nothing. A handful of nearby galaxies, the remnants of what was once a vast and intricate structure surrounded by infinite darkness. They will not know that the universe was once filled with a web. They will not know that galaxies were once connected by filaments stretching across billions of light years. They will not know that there was ever anything beyond their small island of light. The evidence will have faded. The web will have dissolved. And the universe will have returned to the state it was in before the web formed, smooth and featureless, a blank slate. But we are here now, in the brief window of cosmic time when the web is visible. We are living in the era when the universe is at its most structured, its most organized, its most interesting. The web is all around us. It shapes the motion of our galaxy. It determines where galaxies form and how they evolve. It is the reason the universe looks the way it does, and we are only just beginning to map it. Every new survey, every new telescope, every new observation reveals more detail. The filaments become clearer, the nodes sharper, the voids deeper. The web is coming into focus. And with every new piece of data, we are learning how the universe is put together. Not as a random scattering of objects, but as a carefully organized system, a network of structures shaped by forces we cannot see but can measure. The cosmic web is the universe's blueprint. It is the map showing us how everything is connected, and it is telling us that the universe is stranger, larger, and more intricate than we ever imagined. The questions keep piling up. Why did the web form the way it did? Why are the filaments the sizes they are? Why are the voids so large? Why did dark energy turn on when it did? What set the initial conditions? What planted the seeds? The cosmic web is not just a structure. It is a record of the universe's history, written in the distribution of galaxies and dark matter. Every filament, every cluster, every void tells us something about how the cosmos evolved, from the smooth plasma of the early universe to the complex web we see today. And every answer we find leads to more questions. That is what comes next, the unanswered questions, the gaps in our knowledge, the mysteries that remain unsolved. Because as much as we have learnt about the universe, as detailed as our maps have become, we are still missing most of the picture. 95% of the universe is invisible, and the 5% we can see is just the beginning. And here is the strangest part of all. Every mystery we have explored, every anomaly we have uncovered, every contradiction we have stumbled across, they are all connected. The missing matter holding galaxies together, the invisible force tearing the universe apart, the tension in the measurements that refuses to resolve, the vast web of structure threading through space, the Great Attractor pulling us towards something we cannot see. None of these are isolated problems. They are symptoms of the same underlying condition. We do not understand the universe. Not really, not in the way we thought we did. We have built an extraordinarily successful model of cosmology over the past century. Lambda CDM, the standard model, has explained observation after observation with remarkable precision. It predicted the cosmic microwave background and got it right. It predicted how galaxies cluster and got it right. It predicted the relative abundances of hydrogen and helium forged in the Big Bang and got it right. For decades, Lambda CDM has been the gold standard, the framework that tied everything together. And now, as our instruments have gotten better and our measurements more precise, the cracks are showing. The model still works. It still explains most of what we see. But it is failing in ways that cannot be ignored anymore. The Hubble tension, the impossibly early galaxies seen by Webb, the structures that are too large to have formed in the time available, the unexplained acceleration of the expansion, the complete absence of direct detection for the particle that supposedly makes up 85% of the matter in the universe. These are not small problems, these are foundational issues, and they are forcing physicists to confront a possibility that no one wanted to consider. The standard model might be incomplete, or worse, it might be wrong. Let's be clear about what that means. Lambda CDM is not broken in the way a failed theory is broken. It is not phlogiston or the luminiferous aether, ideas that were completely discarded when better explanations came along. Lambda CDM explains too much to be entirely wrong. The cosmic microwave background, the large-scale structure of the universe, the light element abundances, the accelerating expansion, all of that is real, and Lambda CDM accounts for it with a handful of parameters. You cannot throw out a theory that gets that much right, but you can add to it, you can modify it, you can acknowledge that it is incomplete and start looking for the missing pieces. That is where cosmology is right now, standing at the edge of a gap between what the model predicts and what the observations show. And the gap is not closing, it is widening. The problem is not that we lack data. We have more data than ever before. Millions of galaxy redshifts, detailed maps of the cosmic microwave background, gravitational wave detections from merging black holes, high-resolution images of galaxies in the first billion years of the universe. The problem is that the data are not all pointing in the same direction. Different measurements are giving different answers. Different methods are producing incompatible results. The expansion rate measured directly using supernovae says 73. The expansion rate inferred from the cosmic microwave background says 67. Both measurements are precise. Both have been checked and rechecked. Both teams are confident their numbers are correct, and they do not agree. That is not a data problem. That is a model problem. Something in the chain of assumptions connecting the early universe to the present is broken. Either the early universe was slightly different than we think, or the way the universe evolved between then and now does not match our predictions, or the measurements themselves are being affected by something we have not accounted for. Any of those possibilities requires new physics, new particles, new fields, new forces, something that was not in Lambda CDM to begin with. Dark matter and dark energy are placeholders. That is all they are. We call them matter and energy because they have gravitational effects, but we do not know what they actually are. Dark matter could be a new type of particle that interacts only through gravity. It could be primordial black holes left over from the Big Bang. It could be something even stranger, a modification of gravity that mimics the effects of extra mass. Dark energy could be the cosmological constant Einstein predicted a century ago. It could be a dynamic field that changes over time. It could be a sign that general relativity breaks down on the largest scales and needs to be replaced with a more complete theory. We do not know, and that is the point. 95% of the universe is made of things we have names for but do not understand. We can measure their effects. We can map their distribution. We can predict how they behave, but we cannot touch them. We cannot detect them directly. We cannot explain where they came from or why they have the properties they do. We are in the position of astronomers in the 19th century who knew something was perturbing the orbit of Uranus but had not yet discovered Neptune. They could see the effect. They could infer that something was out there. But they did not know what it was until they pointed a telescope in the right direction and looked. We are still looking. The next generation of telescopes and experiments is designed to do exactly that, to look harder, to measure more precisely, to probe the edges of what lambda CDM predicts and see where it breaks. The Euclid mission, launched by the European Space Agency in 2023, is mapping the dark universe with unprecedented precision. Euclid is observing billions of galaxies across more than a third of the sky, measuring how their shapes have been distorted by the gravitational pull of foreground dark matter. The technique is called weak gravitational lensing, and it is one of the most powerful tools we have for mapping dark matter distribution. By analyzing the tiny distortions in the shapes of background galaxies, Euclid can build a three-dimensional map of where dark matter is concentrated and how that distribution has changed over the past 10 billion years. That map will test lambda CDM in ways that have never been possible before. If dark matter clumps together faster than the model predicts, Euclid will see it. If the filaments of the cosmic web are denser or more structured than expected, Euclid will see it. If there are hints that dark energy has changed over time, Euclid will see it. The mission is designed to measure the properties of dark energy to within 1%. That level of precision will either confirm that dark energy is a cosmological constant or reveal that it is something more complicated. Either result is a win. Confirmation means lambda CDM is even more robust than we thought. Deviation means we have found new physics. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will take the search even further. Roman is being built with a field of view 100 times larger than Hubble's, allowing it to survey vast areas of the sky in a fraction of the time. Its primary mission is to study dark energy by measuring the distances and redshifts of millions of galaxies and supernovae. Roman will use multiple independent methods to constrain the expansion history of the universe, cross-checking the results to identify systematic errors. It will also search for gravitational microlensing events, brief flickers of light caused when a dark, compact object, like a primordial black hole, passes in front of a background star. If primordial black holes make up a significant fraction of dark matter, Roman will detect them. If they do not, that rules out an entire class of dark matter candidates. Either way, the data will narrow the possibilities. The Laser Interferometer Space Antenna, or LISA, is a joint mission between ESA and NASA, scheduled to launch in the mid-2030s. LISA is not a telescope, it is a gravitational wave detector, 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers. LISA will detect gravitational waves at much lower frequencies than the ground-based detectors like LIGO and Virgo. Those lower frequencies correspond to signals from supermassive black hole mergers, from the in-spiral of compact objects into supermassive black holes. and potentially from primordial black holes formed in the first moments after the Big Bang. If primordial black holes exist in large numbers, LISA will hear them. The gravitational waves they produce will have a characteristic signature that distinguishes them from black holes formed by collapsing stars. Detecting that signature would be a smoking gun. It would prove that at least some of the dark matter is made of black holes and not exotic particles. It would also raise new questions. How did those black holes form? What does their existence tell us about the conditions in the first fraction of a second after the Big Bang? Why do they have the masses they have? Answering those questions would require new physics, but at least we would know what we were looking for. The James Webb Space Telescope is already delivering data that challenge the standard model. Webb has found galaxies in the early universe that are too massive, too bright, and too well formed to fit the predictions. These are not small discrepancies. Some of the galaxies Webb has observed appear to have formed stars at rates that should have been impossible given the amount of time available. If those observations hold up, and so far they have, lambda CDM will need to be revised. Either the efficiency of star formation in the early universe was much higher than we thought, which requires explaining how and why, or dark matter behaved differently in the early universe than it does today, which requires adding new physics to the model. Both possibilities are on the table. Both are being explored, and both would represent a fundamental shift in how we understand cosmic history. The first billion years of the universe, the era when the first stars and galaxies formed, is no longer a solved problem. It is an active frontier, and Webb is showing us that the frontier is more complicated than anyone expected. Then there are the alternative theories. For decades, the standard model has been so successful that most physicists have been reluctant to consider alternatives seriously. Why look for a new theory when the old one works so well? But the cracks in lambda CDM have opened the door. Some researchers are revisiting modified Newtonian dynamics, or MOND, a theory that proposes gravity behaves differently at extremely low accelerations. MOND was originally proposed in the 1980s to explain galaxy rotation curves without invoking dark matter. It works surprisingly well for individual galaxies. The predictions match the observed rotation curves with fewer free parameters than dark matter models require. But MOND has always struggled with larger structures. It cannot explain galaxy clusters. It cannot explain gravitational lensing. It cannot explain the cosmic microwave background. For years, that was enough to dismiss it. But recently, some physicists have started to wonder if MOND might be pointing towards something real, not as a replacement for dark matter, but as a clue that gravity itself needs to be modified. There are now hybrid theories that combine dark matter with modified gravity, trying to get the best of both. These theories are speculative, they are not widely accepted, but they are being taken seriously in a way they were not a decade ago. The fact that MOND keeps working for galaxies, despite being ruled out on larger scales, suggests that something interesting is happening that the standard model is not capturing. Quintessence, the idea that dark energy is not a cosmological constant but a dynamic field, is another alternative that is gaining traction. If dark energy changes over time, it would explain why the expansion rate appears to be different when measured at different epochs. It would also explain the cosmic coincidence problem, the puzzling fact that dark energy and dark matter have comparable densities right now at this moment in cosmic history. If dark energy were truly constant, why would its density happen to be similar to the matter density at the exact time when intelligent life evolved to notice it? That seems like an absurd coincidence. Quintessence models can avoid that problem by allowing dark energy to evolve in a way that makes the densities converge naturally. The challenge is that most quintessence models predict effects that we have not observed. They change the way galaxies cluster. They change the expansion history in ways that conflict with the cosmic microwave background data. No quintessence model has been able to fit all the observations as well as the cosmological constant does. But the fact that researchers keep trying, keep refining the models, keep searching for versions that work, tells you something. The cosmological constant might be correct, but it might also be a convenient approximation of something more complicated underneath. There is also the possibility that the universe is not homogeneous on the scales we think it is. The cosmological principle, the assumption that the universe looks the same in all directions and at all locations when averaged over large enough scales, is a cornerstone of lambda CDM. It is what allows us to apply the same physics everywhere and assume that measurements made from Earth are representative of the universe as a whole. But the Hercules Corona Borealis Great Wall, a structure stretching across 10 billion light-years, pushes against that assumption. Structures that large should not exist if the universe is truly homogeneous on scales above 1 billion light-years. Either the structure is a statistical fluke, which is possible but unlikely, or the universe is lumpier on large scales than we thought. If the cosmological principle is wrong, even slightly, the entire framework of lambda CDM needs to be reconsidered. The equations assume homogeneity. If the assumption is violated, the solutions change. The expansion rate could vary from place to place. The age of the universe could be different in different regions. The concept of a single Hubble constant might not even make sense. These are radical ideas. They are not mainstream, but they are being discussed in ways that would have been unthinkable 20 years ago. Some physicists have gone even further. The holographic principle, originally developed in the context of black hole thermodynamics, suggests that all the information in a three-dimensional region of space can be encoded on a two-dimensional surface surrounding that region. If the holographic principle applies to the universe as a whole, it would mean that our three-dimensional reality is a projection of information stored on the two-dimensional surface of the cosmic horizon. This is not science fiction. This is serious theoretical physics, developed by some of the most respected researchers in the field. The holographic principle has been applied to cosmology to try to explain dark energy. If the universe is holographic, the accelerating expansion might be a natural consequence of how information is distributed on the boundary. The idea is speculative, untested, and controversial, but it is being explored because the standard explanations for dark energy are so unsatisfying. Saying that dark energy is the energy of empty space does not explain why the energy density is the value it is. It does not explain why it turned on when it did. It does not explain the cosmic coincidence problem. The holographic principle at least offers a framework where those questions might have answers. Whether it is the right framework is another matter. But the fact that physicists are willing to consider ideas this strange tells you how desperate the situation has become. Lambda CDM works, but it does not explain, and physics is not just about predicting what will happen. It is about understanding why. The philosophical implications of all this are profound. For most of human history, we assumed we could see the universe. The stars, the planets, the galaxies, they were all out there, visible, waiting to be catalogued. We built telescopes to see farther, and every time we did, we found more of the same. More stars, more galaxies, more structure. The universe was vast, yes, but it was knowable. Then came dark matter. Then came dark energy. And suddenly, 95% of the universe became invisible. Not hidden behind something. Not too faint to see. Fundamentally invisible, made of things that do not interact with light in any way we can detect. We can infer their existence, we can map their effects, but we cannot see them, and that raises a question that is uncomfortable to think about too hard. If 95% of the universe is invisible to us, what else are we missing? What other forces, fields, particles, dimensions might be out there, shaping reality in ways we have no tools to detect? The history of science is full of examples where a new instrument revealed something no one expected. The telescope revealed moons orbiting Jupiter. The microscope revealed cells. The particle accelerator revealed quarks. Every time we built a tool that could see something new, we found that reality was stranger and more complicated than we thought. And every time, the new discoveries raised more questions than they answered. Why should this time be different? We have just discovered that most of the universe is made of things we cannot see. That is not the end of the mystery. That is the beginning. There is a concept in philosophy called the veil of perception. The idea that we do not experience reality directly, we experience a model of reality constructed by our brains from the signals our senses provide. Our eyes detect a narrow slice of the electromagnetic spectrum. Our ears detect pressure waves in a specific frequency range. Our sense of touch responds to forces above a certain threshold. Everything outside those ranges is invisible to us. We know that ultraviolet light exists because we built instruments that can detect it. We know that radio waves exist for the same reason, but we do not see them. They are not part of our direct experience of the world. Dark matter and dark energy are like that, only more extreme. They do not just fall outside the range of our senses. They fall outside the range of almost every instrument we have built. We can only detect them indirectly by measuring their gravitational effects. And that raises the question, if we are missing 95% of the universe, how much of reality are we missing? How many other things are out there shaping the cosmos in ways we cannot perceive because we do not have the right instruments or the right concepts to even know what to look for? This is not idle speculation. This is a question that physicists are actively grappling with, because the more precisely we measure the universe, the more obvious it becomes that we are looking at a tiny sliver of what is actually there. And the sliver we can see does not make sense on its own. It only makes sense if you assume there is a much larger structure underneath, holding it all together, shaping it in ways we are only just beginning to understand. The next few decades are going to be critical. Euclid is already collecting data. Roman will launch in a few years. LISA will follow in the mid-30s. Webb is observing the early universe right now, finding galaxies that should not exist and forcing theorists to revise their models. The data are coming in faster than ever, and with every new observation the picture is getting clearer. Not simpler, clearer. The universe is more complicated than lambda CDM allows. That is no longer a fringe position. That is the consensus. The question is not whether the model needs to be updated. The question is how. What needs to be added? What needs to be changed? And how do we figure that out when 95% of the universe is invisible? One possibility is that we are on the verge of a paradigm shift. Thomas Kuhn, the philosopher of science, argued that science does not progress smoothly, it progresses in fits and starts. Long periods of normal science, where researchers work within an established framework, are punctuated by revolutions, moments when the framework itself is overthrown and replaced with something new. The shift from Newtonian mechanics to general relativity was a paradigm shift. The shift from classical physics to quantum mechanics was a paradigm shift. Both times, the old theories were not wrong exactly. They were incomplete. They worked in certain regimes but broke down in others. The new theories explained everything the old theories explained, plus more, and they did it with a fundamentally different set of concepts. Maybe that is what is happening now. Maybe the cracks in lambda CDM are signs that we are approaching another revolution. Maybe dark matter and dark energy are not things to be discovered. Maybe they are clues that the entire framework needs to be replaced, that we need a new theory of gravity, a new understanding of space-time, a new set of concepts that make sense of the observations without invoking invisible substances that we cannot detect. That is the dream. That is what every physicist hopes for, a moment when everything clicks, when the data that did not fit suddenly makes sense in a new framework, when the mysteries resolve into a deeper understanding. It has happened before, it could happen again, but it might not. It is also possible that we are just at the beginning of a very long process of figuring out what dark matter and dark energy actually are, that there will not be a single dramatic breakthrough, just slow, incremental progress. More data, better models, narrower constraints on the possibilities. Eventually, after decades of work, we might detect a dark matter particle in a lab. We might measure a deviation in dark energy's behavior that points toward quintessence. We might find primordial black holes with LISA. Any of those discoveries would be a major step forward, but none of them would be a paradigm shift. They would be filling in the details of the framework we already have. That is how most science works. Not dramatic revolutions, just patient, careful, incremental progress. And there is nothing wrong with that. It is less exciting. It does not make for good headlines, but it is how most of our understanding of the universe has been built. One observation at a time, one measurement at a time, one small piece of the puzzle at a time. What is certain is that the next generation of scientists will inherit a universe that is stranger and more mysterious than the one we grew up with. The clean, simple picture of galaxies expanding smoothly apart in a universe made mostly of ordinary matter is gone, replaced by a dark universe, dominated by invisible forces and invisible matter, threaded with structures that are barely allowed by the models, expanding at a rate that no one can agree on. This is the universe we actually live in. 95% of it is missing. The 5% we can see does not make sense without the 95% we cannot. And we are only just beginning to figure out what that means. The questions are bigger than the answers. The mysteries are deeper than the solutions. And that is exactly how science is supposed to work. Every answer raises new questions. Every discovery reveals new mysteries. The universe is not a puzzle that will one day be solved. It is an infinite frontier, and we are still at the edge, looking out into the dark, trying to make sense of the shadows. The missing 95% is not a problem. It is an invitation to look harder, to think deeper, to build better instruments, to ask better questions, an invitation to accept that the universe is stranger than we thought and that our understanding of it is never complete. We will never see the whole picture. We will always be looking through a veil, seeing only the part of reality that our instruments and our theories allow us to access. But that does not mean we should stop looking. It means we should keep pushing, keep measuring, keep questioning, keep searching for the pieces we are missing. Because even if we never find all the answers, the search itself is worth it. Every new discovery, every new measurement, every new piece of data brings us closer to understanding the universe we live in. And that understanding, incomplete as it will always be, is what makes us human. The drive to know, the refusal to accept ignorance, the determination to see what lies beyond the edge of what we can see, that is what science is. That is what drives every mission, every telescope, every experiment. The knowledge that 95% of the universe is out there, waiting, and we are going to find it, one photon at a time, one gravitational wave at a time, one dark matter particle at a time if it takes 100 years. The universe is not hiding from us. It is just bigger, stranger, and more complicated than we ever imagined. And that is exactly why it is worth studying. We started with a number, 5%. The fraction of the universe made of things we can see, touch, measure directly. Everything else, the other 95%, is something we have names for but do not understand. Dark matter holding galaxies together, dark energy tearing space apart. And between those two invisible forces, threading through the cosmos like a skeleton we cannot see, the web. Filaments, stretching across hundreds of millions of light years, voids where almost nothing exists. And us, sitting on a small rock orbiting an average star in a galaxy drifting through one of those filaments, falling toward a point in space we call the Great Attractor, being pulled by gravity we can map but cannot explain. The universe is not what we thought it was. That much is clear. Lambda CDM, the model that has guided cosmology for decades, still works. It still explains most of what we see. But the cracks are showing. The expansion rate does not agree with itself. The early galaxies are too massive. The structures are too large. The measurements refuse to converge. And the more precisely we look, the more obvious it becomes that something is missing. Not just dark matter, not just dark energy, something deeper, some piece of the framework we have not found yet. What happens next is not a mystery. We keep looking. Euclid maps the dark matter. Roman measures the expansion.